Imagine a time when almost every landmass we now know was welded together into a single massive continent, a supercontinent that stretched from pole to pole. This immense block of Earth was called Pangea, and its story reaches back hundreds of millions of years. The roots of Pangea lie in the late Paleozoic era, long before the first dinosaurs roamed the planet. Around 335 million years ago, during the Carboniferous period, two huge continents already existed. Gondwana, which held what today are South America, Africa, Antarctica, Australia, and India, and Laurasia, which comprised the future North America, Europe, and most of Asia. Deep-seated tectonic forces slowly nudged these land masses together. Piece by piece, they closed ancient oceans and fused, forming the continuous land surface known as Pangea. Pangea achieved its most complete shape in the Permian period, roughly between 299 and 200 million years ago. For a span of tens of millions of years, the world's terrestrial surface was dominated by a single landmass, surrounded by a single ocean that lapped at its edges. This golden age of Pangea influenced climate, ocean currents, and the evolution of life, and the massive stresses that folded the crust gave rise to some of the planet's oldest and most impressive mountain ranges. But the forces that assembled the supercontinent eventually turned against it. Beginning in the Jurassic, about 100 to 75 million years ago, fractures appeared on Pangea's surface. These cracks widened into deep rifts, eventually spilling seawater and carving out new oceans. As the rifts expanded, the single continent split into the familiar continents, North and South America, Africa, Europe, Asia, Australia, and Antarctica, that we recognize today. Pangea's rise and breakup are crucial for understanding Earth's geological history. The continent's formation reshaped the planet's crust, set the stage for dramatic climate shifts, and left a legacy of mountain belts and fossil records that still inform scientists as they piece together the deep past of our world. The Appalachian Range in eastern North America, the Caledonian Chain in Europe, and the Urals in Russia all arose from violent collisions of ancient continental plates. Their rugged peaks still bear silent witness to the breakup of the supercontinent Pangea. When Pangea began to split, a dramatic new phase started. Fresh oceans formed. As land fragments drifted apart, molten rock from the mantle rose to create new oceanic crust, especially in the nascent Atlantic basin. This slow continental drift continues today, constantly reshaping the planet's geography. Pangea's climate was extreme. Because the interior lay far from the moderating influence of oceans, there were no maritime winds to temper temperatures. Summers burned, winters froze, and the central regions likely resembled arid, dusty deserts. The surrounding ocean, called Panthalassa, was a vast, deep basin. With few land masses to disrupt currents, warm water could circulate freely along the equator, intensifying heat and driving powerful weather systems, perhaps strong seasonal monsoons that drenched coastal zones while leaving inland areas bone dry. The unified landmass also shaped life's distribution. Animals could roam the whole supercontinent, leaving related fossils on continents now separated by oceans. For instance, fossils of the small freshwater reptile Mesosaurus appear in both South America and Africa, while the pig-sized, semi-mammalian reptile Lystrosaurus is found in Africa, India, and Antarctica. These finds confirm that these regions were once connected. Plants show a similar pattern. The ancient fern Glossopteris, once widespread across Pangea, is recorded in South America, Africa, India, Australia, and Antarctica, areas that today span tropical rainforests to icy tundra. Pangea also set the stage for the Permian-Triassic extinction, the Great Dying, about 252 million years ago, which eliminated roughly 96% of marine species and 70% of terrestrial vertebrates. Scientists debate the cause, citing massive Siberian volcanic eruptions, the harsh supercontinental climate, or a combination of both. As the continents continued to separate, new habitats, mountains, coastlines, and climate zones emerged. Life had to adapt, giving rise to novel species and enriching the diversity of both flora and fauna. Pangea matters because it built much of what surrounds us today. The layout of continents, the shape of mountain ranges, the direction of ocean currents, and even where plants and animals live, all trace back to that ancient supercontinent. It also reminds us that Earth is never static. Pangea wasn't the first supercontinent. Earlier ones, such as Rodinia and Columbia, existed, and it won't be the last. In millions of years, the continents may join again, forming a new supercontinent. Studying Pangea is like taking a ride in a time machine. It lets us see not only a distant past, but also the living, shifting nature of the planet we call home. It shows how everything is linked, how even the largest land masses are part of an endless cycle of change. For most of human history, people believed continents were fixed, immovable pieces of land. The notion that whole continents could drift slowly across the globe seemed so strange that many scientists mocked or rejected it. Yet the idea that once seemed a fanciful fantasy turned into one of geology's core concepts: plate tectonics. This theory explains the most powerful and puzzling Earth phenomena: earthquakes, volcanoes, massive mountain belts, and the spread of ancient life. Plate tectonics says the Earth's outer shell, the lithosphere, isn't a single solid sphere. It's broken into a handful of huge, rigid plates that fit together like pieces of a jigsaw puzzle. These plates glide imperceptibly, moving only a few centimeters each year, about the speed at which nails grow. Some plates carry continents, others form the ocean floor. Where plates meet, three main interactions occur. At divergent boundaries, the plates pull apart. Hot, molten rock rises from deep below, fills the gap, and solidifies into new crust, creating long underwater mountain chains called mid-ocean ridges. At convergent boundaries, the plates crash together. When two continental plates collide, they push up towering ranges like the Himalayas. When an oceanic plate meets a continental one, the denser oceanic slab sinks beneath the lighter continent, carving deep trenches, spawning volcanic arcs, and triggering powerful earthquakes. At transform boundaries, the plates slide past each other. Stress builds along the fault line and releases suddenly as an earthquake. The San Andreas Fault in California is a classic example. What drives all this motion? Deep inside the Earth, the mantle, a thick layer of hot, dense rock, circulates constantly. Heat from the core makes lighter material rise, while cooler, heavier material sinks, creating slow, circular convection currents. These currents tug at the overlying lithospheric plates, pulling them along. The birth of plate tectonic theory was long and uneasy, marked by doubt and debate. Yet today it stands as the unifying framework that ties together the planet's past, present, and future. Alfred Wegener, a German scientist born in 1880, began his career studying weather and the polar regions rather than geology. His keen observation led him, around 1912, to propose the bold idea of continental drift. He noticed that the coastlines of South America and Africa fit together like pieces of a puzzle, prompting the question of whether those continents had once formed a single landmass. Wegener gathered evidence from several fields to support this notion. He pointed out that fossils of the freshwater reptile Mesosaurus appeared only in South America and Africa, a creature that could not have crossed an ocean. Similar fossil matches, such as the plant Glossopteris and various amphibians, were found across Africa, India, Antarctica, and even Australia, suggesting a once continuous continent. He also highlighted the striking continuation of mountain ranges. The Appalachians in eastern North America line up with the Caledonian and Atlas ranges of Europe and North Africa, implying they were once part of the same chain. Paleoclimatic clues reinforced his argument. Wegener showed that glacial deposits existed in parts of India, Africa, and Australia, regions that are now far too warm for permanent ice, while coal deposits, which form in swampy, warm conditions, were present in present-day Antarctica. These findings indicated that Antarctica had once been much closer to the equator. Despite the breadth of his evidence, Wegener's theory was dismissed for decades because he could not explain how continents moved. He suggested they might plow through the ocean floor or be carried by Earth's rotation and lunar attraction. But physicists demonstrated that these forces were far too weak to shift massive land masses. Moreover, as a meteorologist rather than a geologist, Wegener was viewed as an outsider by many in the geological community. The idea remained controversial until the 1950s and 1960s, when a new wave of scientific discoveries, most notably the spreading of the ocean floor, provided the missing mechanism and finally confirmed Wegener's vision of drifting continents. Harry Hess and Robert Dietz proposed that new oceanic crust is continuously created along mid-ocean ridges. Molten rock rises from the mantle, cools, and solidifies, slowly pushing older crust away from the ridge as if on a conveyor belt. The most convincing proof came from paleomagnetism. Iron-rich minerals in the seabed aligned with Earth's magnetic field when they formed, and because the field flips polarity every few 100,000 to a few million years, the ocean floor displays alternating bands of normal and reversed magnetic direction. These bands mirror each other on both sides of the ridge like a barcode, confirming that fresh crust appears at the ridge and spreads outward. Deep-sea drilling later showed that rocks farther from the ridge are indeed older, just as the spreading hypothesis predicted. Modern technology adds further evidence. A global positioning system using a network of satellites high above Earth lets scientists measure the movement of massive tectonic plates with astonishing accuracy, down to a few millimeters per year. By placing receivers on continents and islands, researchers track the slow, continuous shifts of these points, directly observing the drift that plate tectonics theory foretells. Radiometric dating now pinpoints the ages of rock layers, allowing formations on one continent to be matched with identical formations on another, often across an ocean. Such correspondences, together with similar folds, faults, and huge mountain range structures, indicate that continents once joined and later collided. The distribution of volcanoes and earthquake epicenters also supports the picture. They cluster along plate boundaries, exactly where moving plates would interact. Even the ocean floor itself records this history. Samples retrieved by deep water drilling reveal the same patterns of magnetic stripes and age progression that underpin the seafloor spreading model. By studying seismic waves that travel through Earth, scientists can pinpoint a rock's age and origin, and those results line up perfectly with the modern theory of plate tectonics. Today, they employ seismic tomography, a technique akin to taking a gigantic X-ray of the planet. The three-dimensional images reveal hot, buoyant rock rising from the deep mantle and colder, denser slabs sinking back down, exposing the constant motion and mixing of Earth's interior known as mantle convection. This slow, continuous flow of hot and cool material is believed to drive the gradual drift of the lithospheric plates that sit above it. The journey from Alfred Wegener's bold early 20th century hypothesis about drifting continents to the widely accepted theory of plate tectonics stands as one of science's most inspiring stories. It shows how compelling evidence, accumulated over time, can overcome skepticism and resistance. It also reminds us that tackling such problems demands perspectives from geology, physics, chemistry, and even space-based technologies. Plate tectonics is no longer a clever conjecture. It is the foundation of our understanding of the planet's ever-changing surface. It explains the past arrangement of continents and offers clues about their future. More than 300 million years ago, mantle convection gathered the ancient supercontinent Pangea, only to split it later, carving the present continents, oceans, and the pathways that guided the evolution and spread of life. When we look back to Earth's deep past, times so remote they defy modern measurement, one name dominates: Pangea. This massive landmass was the last supercontinent to bring together most of today's continents before its breakup reshaped the world map we know. Yet to truly grasp Pangea, we must travel even further back, because it was neither the first nor the last supercontinent. Throughout billions of years, Earth has undergone repeated cycles in which continents coalesce into a single gigantic block and, after millions of years, fragment again. This supercontinent cycle is powered by the slow stirring of rocks deep beneath the surface within the mantle. Each cycle leaves its imprint in rock formations, mountain ranges, and the magnetic signatures embedded in the crust. By reading these clues, scientists trace the planet's internal dynamics and its rich history. Investigations of earlier supercontinents, such as Pannotia, Kenneland, Columbia, sometimes called Nuna or Rodinia, have revealed a remarkable saga of Earth's surface evolution and the responses of life to these monumental shifts. Our story begins in the Neo-Archean era, spanning roughly from 2,700,000,000 to 2,500,000,000 years ago. It was during this interval that the supercontinent Kenneland likely assembled. Kenneland stands as one of the oldest known supercontinents, its existence supported by robust geological evidence. Imagine a world that, in many ways, resembled our own, but existed in a time when life was just taking its first steps, and the atmosphere we breathe today had not yet formed. The sun may have shone dimly, the early atmosphere contained little or no oxygen, and any life that existed was simple and microscopic. Beneath the surface, however, the forces that move continents were already at work. Kenneland did not arise from the familiar land masses we know today. It assembled from many smaller pieces of crust, ancient cratons that are among the oldest fragments of today's continents. The key cratons that formed Kenneland included the Baltic Shield, now part of Scandinavia and Eastern Europe, the Yavapai craton of present-day North America, and the Ilgan craton of Western Australia. No single intact piece of Kenneland survives in the rock record. Its existence was inferred by comparing very old rocks from different continents and noticing that they once matched. Paleomagnetic signatures locked in those rocks revealed that distant regions had previously occupied the same positions. while matching ages of rock formations, mountain belts, and mineral deposits further supported the reconstruction. Kennel Land marked a major turning point in Earth's history. For the first time, extensive blocks of stable continental crust joined together. Before this, the crust was likely thinner, hotter, and more fragmented, allowing tectonic activity to proceed much faster. The supercontinent shows that billions of years ago, the planet was already shifting toward a slower, more organized plate movement regime, similar to today's. Like all supercontinents, Kennel Land eventually broke apart, a process that probably began about 2,500,000,000 years ago. Scientists think massive mantle plumes, huge upwellings of hot rock pressed against the base of the continent, causing it to stretch, crack, and split. This breakup would have been accompanied by enormous volcanic eruptions that flooded large areas with lava, creating extensive magmatic provinces. As the cratons drifted apart, new oceans formed between them. The disintegration of Kennel Land demonstrated that the supercontinent cycle started long before recent geological times and has persisted through most of Earth's history. It also highlighted how gigantic volcanic events can drive continental fragmentation, a pattern repeated in later supercontinent breakups. Moving forward to the Paleo-Proterozoic era, roughly from 1,800,000,000 to 1,500,000,000 years ago, the remnants of Kennel Land gradually reconvened over hundreds of millions of years, giving rise to a larger supercontinent known as Columbia, sometimes called Nuna. Columbia formed from the collision of many ancient cratons and newer continental fragments, with massive land masses slowly colliding, much like modern continents do today. The collisions that forged the ancient mountain ranges were colossal. Some may have dwarfed anything we see today. The supercontinent Columbia comprised Laurentia, later the core of North America, Baltica, including parts of Scandinavia and Eastern Europe, Siberia, North China, West Africa, and a fragment of Australia. Geologists have identified extensive ancient mountain belts, the orogenic belts, created by these impacts. The most striking example is the Trans-Hudson Orogen, a massive zone of deformed rocks stretching across central Canada and the northern United States. Besides the collision zones, evidence of orogenic magmatism shows volcanic activity that occurred without forming mountains, often during tranquil intervals after the continents had joined. Columbia did not endure forever. Its breakup began roughly 1,500,000,000 years ago. The process was likely slow. The crust fractured during rifting, and new oceanic basins opened in the gaps. This episode is vital for understanding Earth's tectonic evolution, illustrating how plate tectonics grew more pronounced and began to resemble the mechanisms we observe today. The rise and fall of Columbia influenced more than just rocks and mountains. The Great Oxygen Event, when atmospheric oxygen levels rose markedly, predated Columbia. Yet the later stages of the supercontinent may have reshaped nutrient transport in the oceans, fostering the diversification of early eukaryotic cells. Although the era of Columbia is sometimes dubbed the boring billion because few new life forms seem to appear, the prolonged tectonic stability demonstrates how a supercontinent's longevity can steer biological evolution. Our journey now reaches a time well before the dinosaurs, the Neo-Proterozoic era, spanning roughly 1,100,000,000 to 750,000,000 years ago, when the ancient supercontinent Rodinia assembled. If Pangea is the household name of Earth's continental history, Rodinia serves as its enigmatic and powerful predecessor. Its narrative is no less dramatic. Indeed, its breakup triggered some of the most extreme climate episodes, including a snowball Earth, when ice may have blanketed almost the entire planet, followed shortly by the emergence of the first large, complex organisms. Rodinia, named after the Russian word for motherland, was truly immense. Laurentia likely formed its heart, later becoming the core of North America. The supercontinent did not appear instantaneously. Its formation unfolded over millions of years and was tied to the Grenville orogeny, a massive mountain-building event that occurred between roughly 1,300,000,000 and 1 billion years ago. During this interval, several ancient cratons, parts of present-day South America, Africa, Australia, India, and Antarctica, slowly converged and collided, tightly encircling Laurentia. The collision of crustal plates lifted enormous mountain ranges. Though erosion has worn the peaks away, deep roots of those ranges still appear on distant continents, proving they once formed a single landmass. How do we know this supercontinent existed? Geologists have gathered evidence worldwide. Paleomagnetic data show where rocks lay when they formed, and similar rock types and structures are found on far-apart continents. For example, Grenvillian rocks in eastern North America match those in Scandinavia, the British Isles, and even Antarctica, indicating the continents were once united as Rodinia. Rodinia's story did not end with its assembly. Its breakup began about 750 million years ago and lasted several hundred million years, a turbulent epoch. Scientists think mantle plumes, massive upwellings of hot material, pierced the supercontinent, creating new coastlines and shallow seas. Exposed land eroded quickly, and chemical weathering removed carbon dioxide from the atmosphere. With less greenhouse gas, the climate cooled sharply. Early volcanic activity may have briefly warmed the planet, but it could not stop the deep glaciation that likely covered most of the globe. That ice age set the stage for new evolutionary steps. Harsh, frozen conditions probably drove life toward greater complexity, giving rise to the first large, multicellular organisms of the Ediacaran biota, which later sparked the Cambrian explosion and an unprecedented burst of biodiversity. Thus, the rise and fall of Rodinia reshaped both the planet and the direction of life. Rodinia was not the only ancient supercontinent. Earlier came Kennerland and Columbia. All three belong to a larger supercontinent cycle, in which continents gradually merge into massive landmasses and later split apart, each cycle lasting 300 to 500 million years. Two main models explain new supercontinent formation. The inversion model posits that a new supercontinent appears when internal oceans, remnants of a previous breakup, close. The exversion model suggests continents travel around the globe and meet on the opposite side, sealing external oceans. Regardless of the model, the pattern repeats. Continents join, heat builds beneath, they rift again, and the fragments drift until they collide anew. This cycle influences not only continental outlines, but also climate, sea level, ocean currents, and even the evolution of life, with interior regions of a supercontinent often becoming hot and dry due to their distance from the sea. Ocean currents intersect and change direction, so warm water spreads across the globe in new ways. This shift can trigger major climate swings. At the same time, the planet's reflectivity, its albedo, also varies, because the balance between ice and land decides how much sunlight is bounced back versus absorbed. The rise and fall of supercontinents drive the carbon cycle. When a supercontinent breaks apart, volcanic activity ramps up, spewing carbon dioxide into the atmosphere and heating the planet. Freshly exposed land then weathers, pulling carbon dioxide out of the air and cooling the climate, sometimes to the extent of snowball Earth conditions. Continental drift reshapes the ocean floor. As plates pull apart, seafloor spreading zones grow, pushing water upward and raising sea level. When the plates converge again, spreading slows, water is displaced outward, and sea level falls. Life follows this rhythm. Moving continents create new habitats and erase old ones, which can lead to mass extinctions or bursts of rapid evolution. Rift zones that form shallow seas become fertile grounds for marine diversity, much like the thriving ecosystems that appeared after earlier continental breaks. These same tectonic forces also concentrate valuable mineral deposits. Many important ores formed either under the crushing pressure of continent collisions or during magmatic intrusions that accompany rifting. Every ancient supercontinent has taught geologists a distinct lesson. The earliest, often called Cannerland, illustrates the initial stabilization of Earth's crust. Later, the continent of Columbia showed how these processes laid the groundwork for modern plate tectonics. The final and most dramatic example, Rodinia, demonstrated how deep Earth forces can remodel the surface and influence life itself. The story of Pangea, the massive supercontinent that once gathered almost all of Earth's land, is more than a tale of rocks and plates. It is a cornerstone of the planet's biological history. Pangea did not appear overnight. Its formation was the result of a long, dramatic journey that stretched over hundreds of millions of years. To understand that journey, we must travel back to the Paleozoic era, which began about 541 million years ago and ended around 252 million years ago. This interval is often called the Age of Ancient Life because it was marked by rapid evolutionary leaps, sharp climate swings, and restless continents that drifted, collided, and reshaped the world's face. At the start of the Paleozoic, Earth's surface looked very different. The continents were broken into many smaller pieces, remnants of the far older supercontinent Rodinia, which had already fragmented. Among these fragments, two gigantic land masses, Gondwana and Laurentia, stood out as the main players in the future configuration of the planet. As the era progressed, these massive blocks drifted toward each other. Their eventual collision gave rise to the supercontinent known as Pangea. While the continents were on this slow, grand dance, life made a decisive leap from simple marine organisms to complex plants and animals that conquered the land. Towering forests rose, strange sea creatures flourished, and early reptiles began the path toward dominance. Thus, the tectonic choreography of drifting, colliding, and re-splitting continents not only sculpted the planet's geography, but also set the stage for the major biological transformations that define Earth's history. Gondwana didn't appear in the current era. It formed long before, in the Neo-Proterozoic, breaking away from the remnants of Rodinia. At its height, it was the largest landmass on Earth. Its future pieces would become South America, Africa, Antarctica, Australia, India, Madagascar, the Arabian Peninsula, and even parts of Florida and southern China. Around 541 million years ago, Gondwana lay mostly in the southern hemisphere, with a substantial portion near the South Pole. Imagine that massive continent drifting northward for millions of years, like a colossal ship crossing the globe. This steady movement reshaped the planet. As Gondwana moved into warmer latitudes, its interior turned arid and desert-like, while its margins and coastal zones hosted lush, thriving ecosystems. Evidence of its ancient polar position comes from deep glacial scratches and striations found in places such as India and Africa, confirming that huge ice sheets once covered the supercontinent. Fossil plants, especially the widespread Glossopteris, appear on several modern continents, proving those lands were once joined. Gondwana also altered ocean currents, wind patterns, and global climate, deciding where rains fell and where deserts formed. While Gondwana dominated the south, the early Paleozoic northern half resembled a patchwork of smaller blocks. Laurentia, the core of present-day North America and Greenland, Baltica, today's Scandinavia and parts of Eastern Europe, Siberia, and Avalonia, parts of Eastern North America, Britain, and Ireland. Unlike the unified Gondwana, these northern fragments drifted independently. Over time, they began to converge, eventually welding together into the northern supercontinent Laurasia. This collision occurred later in the Paleozoic and was accompanied by dramatic geological events, massive continent-to-continent impacts that reshaped the Earth's surface. As the blocks merged, each passed through different climate zones, giving rise to unique flora and fauna distinct from those that lived on Gondwana. Those biological differences highlight how isolated the continents were before the formation of Pangea allowed northern and southern species to mix. The whole Paleozoic era can be visualized as a slow, grand dance in which continents moved like cautious dancers toward a final embrace. That climax was the assembly of Pangea, achieved not by a single impact, but by a series of monumental events. One of the earliest major collisions was the Caledonian orogeny, which unfolded during the Silurian and Devonian periods, roughly from 440 to 390 million years ago. During this time, Laurentia, Baltica, and Avalonia inched closer together, sealing the ancient Iapetus Ocean that lay between them. When the land masses finally slammed together, they thrust up enormous mountain ranges, setting the stage for the later formation of the supercontinent Pangea. Remnants of those ancient ranges can still be seen today in the Appalachians of eastern North America, the Scottish Caledonides, the Scandinavian mountains, and parts of Greenland. Their collision created a new northern supercontinent, often called Euro-America-Laurasia. A key phase of the Caledonian mountain building was the Acadian orogeny of the Devonian, when the oceanic plate slammed into Laurentia, raising fresh peaks and tightening the bond between the northern continents. The last and most dramatic encounter happened during the Carboniferous and Permian, roughly from 320 to 250 million years ago. Then the two giants, Gondwana and Laurasia, finally collided on a planetary scale. This era produced two major uplift events, the Eligian and the Variscan, also known as Hercynian orogenies. The Eligian orogeny resulted from the massive collision of Africa, then part of Gondwana, with eastern North America belonging to Laurasia. That clash lifted the Appalachians, leaving the rugged backbone that survives today. At the same time, the Variscan orogeny unfolded as Africa and smaller fragments struck Europe, creating the mountain systems of Central and Southern Europe, including early versions of the Alps, the Pyrenees, and the Urals. These impacts not only forged mountains, but reshaped the crust, sparked intense volcanism, and reconfigured the planet's structure. Layer by layer, they eventually welded all major land masses into the colossal supercontinent Pangea, which stretched from pole to pole and was encircled by the vast ocean Panthalassa. While continents drifted and merged over hundreds of millions of years, life underwent equally dramatic changes. This great chapter is called the Phanerozoic Eon, spanning roughly from 541 to 252 million years ago. It was an era of both moving land and flourishing life, which colonized land and suffered several devastating extinctions. The story begins in the Cambrian, about 541 million years ago, with the Cambrian explosion. Seas teemed with new organisms. Almost all major animal groups with backbones, shells, and hard parts appear in the fossil record within a short geological span. The surge stayed marine, thriving in shallow seas, especially on newly exposed continental shelves that formed after the breakup of the older supercontinent Rodinia. Those nutrient-rich shallow waters became ideal cradles for life's expansion. Rodinia entered the Ordovician, lasting from 485 to 443 million years ago, when ocean life grew more diverse. The first vertebrates, early fishes, appeared, and toward the end of the period, plants began to colonize land. These simple, non-vascular plants marked a turning point. The Cambrian ended with a catastrophe, one of the earliest mass extinctions. Scientists think it may have been triggered by the drift of the massive southern continent Gondwana across the South Pole. The glaciations lowered sea level and wiped out many marine species. After them came the Silurian, a time of expanding land. Jawed fish appeared, a key step, while plants spread across continents, developing vascular systems that let them grow taller. The first terrestrial animals followed. Tiny myriapods and scorpions colonized moist soil. Shifting continents reshaped ocean currents, creating new habitats and driving evolution. The Devonian, about 400 million years ago, is called the Age of Fishes. It produced many new fish, some armored, some jawed, some beginning to breathe air. The greatest breakthrough was the first amphibians, vertebrates that left water for land, beginning the conquest of dry ground. The first forests of tall, tree-like plants appeared, stabilizing soils and forming the basis for later ecosystems. The Carboniferous, roughly 350 to 300 million years ago, featured vast, swampy forests covering much of the northern supercontinent Laurussia. When trees died, they were buried and turned into the coal we still use. Amphibians diversified, and the first reptiles laid eggs on land. The collision of Laurentia and Baltica created the supercontinent Euramerica, raising oxygen levels and allowing insects like giant dragonflies to grow huge. The Permian, from 300 to 250 million years ago, marked the Paleozoic climax. The supercontinent Pangea united almost all land, and reptiles spread across its dry interior. Changes in ocean circulation, mountain uplift, and a harsher climate set the stage for the greatest extinction, the Permian Triassic event, which eliminated about 90% of marine species and 70% of terrestrial vertebrates. The leading hypothesis links it to eruptions forming the Siberian traps, which released huge amounts of greenhouse gases, warming the planet, poisoning the oceans, and collapsing ecosystems. Some scientists argue that the very formation of Pangea may have disturbed the planet's internal dynamics, worsening the ensuing catastrophe. Throughout the Paleozoic era, the Earth's environment constantly shifted. Warm intervals gave way to glacial periods, especially during the Rhodovec and Carboniferous times, when expanding ice sheets lowered sea levels. As plants proliferated in the Carboniferous, atmospheric oxygen rose, not only sustaining new life forms but also enabling some organisms to attain remarkable sizes. Oceanic currents and the gradual collision of continents reshaped water flow, nutrient distribution, and the habitats of countless species. Yet this zoic interval was far more than a prelude to dinosaurs. It was an epoch of monumental change. Over hundreds of millions of years, life progressed from tiny marine organisms to terrestrial animals and towering forests. The Earth's crust behaved like a giant, living mosaic, its pieces drifting slowly under the force of deep mantle currents. Gondwana and Laurasia inexorably approached one another, their slow-motion collision eventually forging the supercontinent Pangea and redefining the planet's layout. Picture the planet's surface not as a rigid shell, but as a vast, moving mosaic. This image underlies plate tectonics, a revolutionary idea that reshaped our understanding of Earth. The lithosphere, the outermost layer, is split into several tectonic plates that glide atop the softer, almost fluid mantle beneath. Though they advance only a few centimeters each year, this patient drift generates the most powerful geological features. Plates interact in three main ways. They pull apart at divergent boundaries, slide past each other at transform boundaries, and, most dramatically, converge at collisional boundaries. When two massive continental plates meet, the encounter is far from gentle. It is a collision that remodels the planet over tens of millions of years. These titanic forces erect the world's highest mountain ranges and carve deep scars that preserve the story of ancient supercontinents like Pangea. At transform zones, the interaction resembles trying to sink two large plugs into a bucket of water. Both remain afloat, resisting subduction. Typically, denser, thinner oceanic crust will plunge into the mantle when it meets another plate, but thick, buoyant continental crust refuses to sink. Consequently, rocks caught between converging continents are uplifted, folded, and broken, accumulating into towering ranges. Geologists call this process orogeny, mountain building. Beneath each mountain lies a thickened crustal root that extends deep into the mantle, akin to a hidden keel. This deep root supports the massive edifice and participates in isostasy, the slow rise and fall of mountains as erosion, glaciation, and load redistribution reshape them. One of the most renowned mountain belts born from Pangea's assembly now stretches across the eastern part of present-day North America. Today, the rounded, gentle slopes of the Opal Mountains look modest next to the sharp peaks of the Polish Himalaya range. But that appearance is deceptive. Once, these soft hills were part of a truly massive mountain system that could rival the height of the Himalayas. The Opal Range did not arise in a single event. It formed through a long series of continental collisions lasting hundreds of millions of years. The most crucial of these collisions occurred during the Aeolian orogeny, roughly between 320 and 280 million years ago. At that time, the ancient continent Laurentia, an early version of North America, pressed against Gondwana, the great southern supercontinent that included present-day Africa. Yet powerful tectonic activity had already taken place long before the Aeolian episode. Earlier orogenies, known as the Taconian and Ocasian folds, accompanied the opening of the ancient Epete Ocean and the impact of small volcanic islands and microcontinents on Laurentia. Those early collisions laid the groundwork, but the Aeolian folding delivered the final, thunderous blow that fully expressed the force of converging plates. During this massive clash, existing rock layers were bent, fractured, and thrust westward. Gigantic sheets of rock, dozens of kilometers thick, slid horizontally over one another for hundreds of kilometers, creating what geologists call a thrust-fold belt. This process gave birth to the Opal Mountains. The Aeolian front marks the outer edge of this colossal deformation, the visible line beyond which the Earth's crust was radically restructured. The scale of the Aeolian orogeny is hard to imagine. Estimates suggest that the ancient Opal peaks may have risen 7.5 to 9 kilometers, rivaling today's Himalayas.
The range stretched for several thousand kilometers, forming the central spine of the newly assembled supercontinent Pangea. Over subsequent hundreds of millions of years, wind, water, and ice wore down the highest summits, yet the underlying stone skeleton endured.
Parallel ridges and deep central and southern valleys preserve the remnants of those massive folds and thrusts, while the interior of the mountains contains metamorphic rocks, slates, phylites, and gneisses that endured intense heat and pressure during mountain building. To the west, in adjacent basins, lie thick deposits of eroded material, sandstones, clayey slates, and conglomerates that form the so-called foreland basins, sedimentary layers that are the washed-away remnants of once towering peaks. Looking across the Atlantic to Russia reveals a comparable story in the Ural Mountains. These rugged peaks extend more than 2,400 kilometers from the Arctic Ocean in the north to the Ural River in the south. Like the opals, the Urals arose from the massive reconfiguration of Pangea between 320 and 250 million years ago, when the Baltic continent collided with the Siberian continent and a smaller Kazakh bloc. Previously, the area was split by the narrow Ural Ocean. As its floor was gradually subducted and disappeared, the continents finally slammed together, forging a mountain chain. The Urals, too, consist of folded and broken layers of sedimentary, igneous, and metamorphic rocks, their long, narrow shape reflecting the tight zone of ancient collision. However, the Ural range has been preserved in a somewhat different manner. Unlike the humid climate of the Opalaki region, the Urals have long endured a drier continental environment, which helped preserve many of their original features, even though erosion has worn them down over time. Both the Opalaki area and the Urals stand as ancient monuments to the slow, massive forces of tectonics, a silent chronicle of a planet where whole continents once drifted, collided, and rose toward the skies. The Ural Mountains stretch far beyond a simple Europe-Asia border. Their rocks tell a dramatic tale of Earth's deep past, recorded in stone. Careful study shows that the Urals were born from a colossal clash of huge pieces of the crust, much like two ships smashing together and shattering on impact. The strongest proof comes from the presence of ophiolites, fragments of ancient ocean floor and underlying mantle that were thrust upward onto the continent. Such a scenario could only happen when a vast ocean closed, its seabed compressed and forced onto land, indicating that millions of years ago, a great ocean covered the area now occupied by the Urals. Beyond their geological intrigue, the Urals are exceptionally rich in natural treasures. Beneath the peaks lie glittering gold veins, platinum nuggets, copper and nickel deposits, and even precious gemstones. These riches were not random. They formed during the intense mountain building process when soaring temperatures and pressures drove mineral-laden hydrothermal fluids through cracked rocks, depositing metals in concentrated clusters. This is why the Urals have long been known as one of Earth's most valuable ore belts. In a broader sense, the Urals resemble a scar on the planet's surface, a visible line where two once separate landmasses, ancient Asia and ancient Europe, were sewn together. This seam marks the collision that created the eastern edge of the supercontinent Laurasia, later becoming a key part of Pangea, which united almost all land on Earth. The Urals are only one piece of that grand story. During Pangea's formation, similar mountain systems rose worldwide: the Appalachians in North America, the Hercynian-Variscan chain stretching from Spain and France through Germany to the Czech lands, and the Anti-Atlas in North Africa.
If we could rewind time and reassemble the ancient Pangean puzzle, we would see these ranges, today scattered across continents, once forming a single, colossal mountain chain. The central Pangean mountain belt stretched across the heart of the ancient supercontinent like a massive spine, becoming one of the most striking features of its time. Towering peaks, highlands, and long ridges ran for thousands of kilometers, steering winds, channeling rain, and shaping the climate in ways still visible today. Pangea's formation was more than a rearrangement of land. It reshaped Earth's whole environment. The gigantic continent covered so much of the planet's surface that regions far from the sea turned dry and harsh. In the interior of Pangea, scorching summers met bitterly cold winters, with no nearby seas to moderate temperatures, so seasonal swings reached extremes. Arid conditions encouraged deserts and salt flats to spread, with thick layers of evaporite minerals later accumulated. Near the equator, the picture was completely different. Moist, low-lying basins supported dense, humid forests of towering trees and ferns. Over millions of years, dead plants collected and were buried, eventually forming the massive coal seams still mined today, direct legacies of Pangea's lush equatorial climate. The supercontinent also altered the oceans. As the continents drew together, ancient seas sealed off, leaving the landmass surrounded by a single, vast ocean called Panthalassa. This new ocean reshaped water movement worldwide. Currents changed direction, redistributing heat and nutrients, forcing marine life to adapt, with some species emerging and others disappearing. The rise of the supercontinent lifted enormous mountain ranges. Over millions of years, these ranges eroded, delivering sediments and dissolved minerals into the seas, likely affecting ocean chemistry and influencing marine evolution. The story of Pangea rests on the astonishing power of tectonic plates, hundreds of kilometers thick, slowly colliding over hundreds of millions of years. The mighty ranges that arose, such as the Urals and the Appalachians, are not just scenic landscapes. They are the scarred remnants of ancient continental battles, proof that the planet is in constant motion. Studying these mountain-building phases helps us understand not only Earth's surface, but also the deep processes that drive continental drift, ocean redistribution, mountain formation, and even the course of life itself. Pangea was more than a supercontinent. It was a turning point that affected weather, climate, evolution, and mass extinctions. The Earth is not a static slab, but a living, breathing world, its history etched in stone, and its future written by the slow, relentless shifts beneath our feet. The concept that today's continents once formed a single, colossal landmass remains one of the most captivating chapters in Earth's past, turning what once seemed like science fiction into a well-supported scientific reality. Scientists needed hard, repeatable answers about the Earth's deep past. When the continents first stuck together and what proof shows Pangea really existed were questions that took decades to answer. Like detectives unraveling an ancient mystery, geologists examined rocks, fossils, and traces hidden deep beneath the surface. Piece by piece, evidence built up. Today, most researchers agree that the supercontinent Pangea finally coalesced about 335 million years ago during the Carboniferous period. The actual joining happened quickly, even though the land masses had drifted slowly for millions of years, colliding and welding together through massive tectonic forces. That single, enormous block reshaped climate, flora, and fauna across the globe.
To pinpoint when and how this happened, scientists acted like crime scene analysts. They studied rock orientations, ancient fossils, and the hidden patterns of Earth's magnetic field. Paleomagnetism, the study of ancient magnetization locked in rocks, provided one of the strongest clues. When certain rocks solidify, the magnetic minerals within them align with the planet's field, acting like tiny frozen compasses. By comparing rocks of different ages from various continents, researchers could trace each piece's former movement. When the continents were arranged into the outline of Pangea, the magnetic data from all of them matched perfectly, showing a shared magnetic history that could only exist if the continents had once been joined. Ocean floor studies added further proof. Mid-ocean ridges, where new crust forms, record the magnetic field as molten rock cools, just like terrestrial rocks do. The symmetrical magnetic stripes on either side of these ridges demonstrate that the seafloor has spread outward for millions of years, pushing continents apart. If today the continents are pulling away, they must have been much closer, or even united, in the distant past. Land-based evidence reinforced the picture. Matching mountain ranges, rock layers, and structural features appear on opposite sides of the Atlantic. The Appalachian chain in eastern North America aligns seamlessly with the Hercynian mountains of Central and Southern Europe and the Anti-Atlas Range in northwest Africa, together forming the Central Pangean orogenic belt. Their outlines, rock types, folds, and faults correspond as if the two halves had been cut and then sewn back together. Studies of ancient cratons, the most stable, oldest parts of continents, also matched. The Canadian Shield of North America fits exactly with the Baltic Shield of Europe and the West African craton, like pieces of a global jigsaw puzzle. Finally, the patterns of ancient glacial deposits further corroborate the reconstruction, showing that ice sheets once covered a continuous landmass that later split apart. All these independent lines of evidence, magnetic signatures, seafloor spreading, mountain range fits, craton alignments, and glacial records, converge on a single conclusion. The continents were once joined in the supercontinent Pangea, later broken apart by the relentless motion of Earth's tectonic plates. Scientists have uncovered ancient glacial deposits, till, striations, and U-shaped valleys in faraway modern regions such as South America, Southern Africa, India, Australia, and Antarctica. At first, the finds seemed inexplicable, because these areas are now warm and tropical, far from any place where ice sheets could form. When the continents are pieced back together into the southern part of the ancient supercontinent Gondwana, the picture becomes clear. All those sites once circled the South Pole, where massive ice caps naturally existed. This evidence was among the earliest and most convincing proofs of continental drift. The rocks also reveal the climate of that distant era. During the Carboniferous, when the land masses were joining to become Pangea, vast swampy forests stretched along the equator, leaving thick coal seams that we still mine today in North America, Europe, and parts of Asia. If those coal-bearing swamps are positioned back at the equator, the warm, humid conditions that fostered their growth make perfect sense. On the opposite side of the ancient continent, dry regions produced evaporites, salts, gypsum, and red beds rich in iron, features we now find in the interior of the former Pangea. Their distribution only fits a scenario where the continents were once joined. Fossils provide equally striking clues. Glossopteris, a fern-like plant with hefty, tongue-shaped leaves, produced seeds too heavy to travel long distances by wind or water. Yet its fossilized remains appear in South America, Africa, India, Australia, and Antarctica. The only logical explanation is that these lands were once connected, allowing the plant to spread without crossing oceans. Another telling discovery is a small freshwater reptile about 1 meter long that lived exclusively in rivers and lakes and could not survive in salty water. Its fossils have been found only in southern Africa and eastern South America. Today, those regions are separated by thousands of kilometers of ocean, but the creature's limited range suggests they were once neighboring parts of a larger landmass. All of this magnetic, geological, and paleontological evidence converges on a single picture. Roughly 335 million years ago, in the Carboniferous, Earth's continents slowly collided to form the mighty supercontinent, Pangea. This monumental event reshaped the planet, creating today's mountain ranges and the ancient ecosystems that once thrived on a single, continuous continent. One of the clearest pieces of evidence for the ancient supercontinent Pangea comes from the terrestrial reptile Lithospheric. This plant-eating animal, about the size of a modern pig, lived during the late Permian and early Triassic, roughly 252 to 248 million years ago. Unlike its relative Mesosaurus, Lithospheric never swam. It walked on land and could not cross oceans. Yet fossils of the same species have been found in 3 far-apart locations: Antarctica, India, and southern Africa. The fact that one land-bound creature inhabited all 3 continents shows that those lands were once joined. They formed part of the massive southern portion of Pangea called Gondwana. The age of the Lithospheric fossils matches the time when geologists believe Pangea had completely assembled, strengthening the argument. Another terrestrial reptile, the Cynagnathian, was about the size of a dog and, like Lithospheric, could not swim across seas. Its remains have turned up in both South America and Africa, again indicating that these continents were once a single landmass. Similar matching fossil records have been discovered across today's widely separated continents for other ancient amphibians, early mammals, and primitive plants. Many of those organisms lived only on land or in fresh water and could not have crossed the vast oceans that now separate the continents. These converging fossil data tell a clear, sequential story. In deep time, the continents were linked into one enormous supercontinent. The case becomes even more persuasive when it is combined with other lines of evidence. Scientists have examined the directions of ancient magnetic fields preserved in rocks, paleomagnetism, matched rock layers and mountain ranges across continents, and studied ancient climate patterns. All of these investigations point to the same conclusion: Pangea truly existed. Pangea formed about 335 million years ago, during a period of massive geological change. Its assembly triggered widespread mountain building, altered atmospheric and oceanic circulation, and profoundly influenced the evolution of life. Plants and animals could spread across the vast, continuous land, and new species emerged in response to the altered environments. The fossil record opens a window onto that ancient world, letting us imagine a time when creatures like Lithospheric roamed lands that are now divided by oceans. It is more than a dry scientific fact. It reminds us that Earth is constantly moving. The continents drift, collide, and reshape the planet over millions of years. The final formation of Pangea was a pivotal moment that set the stage for the planet's later physical appearance and the development of life itself, a vivid example of a living Earth in perpetual motion. Because a single massive landmass once covered almost the entire globe, the ancient supercontinent Pangea dominated the planet for tens of millions of years. At its core lay a region unlike anything we see today, a vast, hostile interior far from any ocean. Without the moderating influence of sea breezes and humid air, The heart of Pangea became a furnace of scorching heat, piercing cold, and relentless drought. Imagine the sheer size of Pangea. No modern continent even comes close. It stretched from icy northern poles to frozen southern lands, incorporating almost every piece of continental crust. Today, continents like Asia and Africa are surrounded by oceans that temper temperature and deliver rain. But Pangea lacked that buffer. Its sheer breadth pushed the continental climate to extremes that are hard to picture now. Moist air from the surrounding seas had to travel thousands of kilometers across dry land to reach the interior. Along the way, it lost most of its moisture. Even if any reached the center, it arrived dry and dusty. Adding to the aridity were the enormous mountain ranges that rose when separate land masses collided. Picture the ancient equivalents of North America's Appalachians, Scotland's Highlands, and the towering ranges that once spanned Europe and North Africa, some as high as, or higher than, today's greatest peaks and stretching for thousands of kilometers. These ridges acted as massive stone barriers, forcing oceanic winds upward. As the air rose, it cooled, shedding rain or snow on the windward slopes, creating isolated green oases. On the leeward side, the descending air turned hot and dry, casting a rain shadow that extended for thousands of kilometers. These shadows didn't just dry the ground. They birthed endless deserts unlike any we have now. The interior deserts sprawled with red and golden dunes that fierce winds constantly reshaped, burying ancient landscapes one moment and exposing them the next. Some areas resembled the Sahara or Arabian deserts, but on a far larger scale. Elsewhere, broad stone plains and high plateaus stretched under a sky where almost nothing grew. Occasional brief rains formed tiny lakes or inland seas, only to evaporate quickly under the relentless sun, leaving shimmering salt flats that stretched to the horizon. The land often glowed in reds and oranges as iron-rich rocks reacted with oxygen. In short, Pangea's massive size, isolation from oceans, and towering mountain chains created an interior of extreme heat, severe cold, and vast, ever-shifting deserts, a world of stark contrasts that defies modern comparison. Red-colored sedimentary layers that geologists now read as evidence of ancient deserts formed under the extreme climate of central Pangea. With no large lakes to store daytime heat and release it at night, temperatures swung wildly. Days were blisteringly hot, deadly for most life, while nights could plunge into frost. This daily heat-cold swing repeated almost every day, and the seasons only amplified the extremes. Summer was scorching, winter bitterly icy. The air stayed dry, often choked with dust lifted by relentless winds. Pangea's impact wasn't limited to its interior. As a single, massive continent surrounded by a global ocean, it reshaped atmospheric and oceanic circulation. In the hot months, the land warmed faster than the sea, creating a huge low-pressure zone that sucked in moist marine air. The result was super monsoons, seasonal wind systems far more powerful than any modern monsoon. Coastal regions could receive heavy rain, but the interior rarely saw precipitation. By the time the air reached the continent's heart, clouds had dumped almost all their moisture, leaving the desert parched. Winter reversed the pattern. The land cooled quickly, forming high-pressure areas that pushed cold, dry air outward, intensifying continental aridity. The constant back and forth of these massive air masses produced chaotic, powerful global weather patterns. It's hard to overstate how harsh and strange Earth's climate was in that era.
The interior of Pangea was a world of extremes: lethal heat, fierce cold, endless deserts, towering mountains, dust storms, and forgotten inland seas.
The rock record tells us that this supercontinent dramatically molded Earth's climate and left a deep imprint on planetary history. Pangea's surface was a patchwork of open plains, high plateaus, deep valleys, and varied basins. A giant mountain belt ran across the north and central regions, but between the peaks lay vast lowlands. Some basins were dry and dusty, while others occasionally hosted small seas or temporary lakes during warmer periods when the water cycle intensified. Depending on elevation and proximity to moisture sources, these basins could fill seasonally, forming inland seas or extensive saline lakes, only to dry out later and leave evaporite crusts as proof of past aridity. The Permian period, lasting from roughly 300 to 250 million years ago, saw the first stresses on Pangea that would eventually lead to its breakup. In parts of the crust, slow stretching and thinning opened the first cracks in the supercontinent. Early rift valleys were long, low depressions that sometimes filled with water, forming narrow lakes or seasonal streams. When a rift became deep enough, magma could rise to the surface and trigger volcanic activity, especially far from the coasts. Most of the big volcanoes, however, remained on the margins of Pangea, near zones where oceanic crust was forced beneath the continent in subduction zones. The river system of Pangea was extraordinary. The continent stretched almost from pole to pole, so moving water across its surface required gigantic rivers. Many of these rivers never reached the sea. They emptied into interior basins where the water evaporated, leaving flat, dry lake beds, playas, or sparkling salt flats. Only a few rivers that did reach the ocean were truly massive, draining huge portions of the land and traveling great distances. Because the supercontinent had very few outlets for rainwater, its overall water cycle differed from today's, and interior erosion even affected ocean chemistry. The climate of that era was both strange and harsh. Carbon dioxide levels were considerably higher than now, providing a general warmth, but the heat was unevenly spread. The sheer size of Pangea caused slow heating and cooling, thermal inertia, so the equator stayed hot while the poles remained cold, creating large temperature gaps and sharp seasonal swings. Although the poles were part of the same landmass, they likely endured long, bitter winters and seasonal ice sheets, yet they were far less glaciated than during the earlier Carboniferous period. Evidence from scattered rocks supports this picture. Coal seams, which form in warm, swampy settings, appear only in narrow strips along Pangea's fading edges, indicating that the interior was too dry for dense forests and swamps. Central and subtropical zones are marked by red beds and extensive salt deposits, evidence of vast deserts. Without the moderating influence of surrounding oceans, the interior suffered extreme aridity, strong winds, and rain shadows behind huge mountain ranges. The sheer size of the supercontinent generated winds and weather patterns that affected the whole planet. Life there had to cope with scorching summers, freezing winters, drought, and limited water, demanding endurance, ingenuity, and special adaptations. Today, the rocks of Pangea scattered across modern continents form a mosaic that records this ancient world. They reveal not only the shape of the land, but also how climate and geography together shaped the destiny of life. She reminds us that a continent's shape and size can set the rhythm for an entire planet. The Permian, stretching from about 299 to 252 million years ago, marks one of the most dramatic chapters in Earth's long story.
During this interval, the supercontinent Pangea finally snapped together into a single, massive landmass, reshaping the world's face. As the continents locked like giant puzzle pieces, oceans, wind patterns, and water cycles began to shift, and life, walking, crawling, swimming, growing, had to adapt. Early in the Permian, terrestrial life still felt the legacy of the Carboniferous's endless swamps and gigantic insects. Moist, coal-bearing marshes teemed with early amphibians, while towering primitive trees such as lycopsids, seed ferns, and sphenopsids formed dense, waterlogged forests that later compressed into today's coal seams. But as Pangea solidified, the global climate grew drier and more extreme, increasingly ruled by seasonal changes. Rainforests receded, deserts spread, and organisms faced a stark choice: adapt quickly or disappear. Along riverbanks and damp coastlines, remnants of the ancient swamp flora lingered.
Massive ferns and club-like plants still thrived in wet soils, but they gradually yielded to gymnosperms, conifers, cycads, and ginkgos, better suited to the arid, harsh plains of Pangea. These seed-bearing plants gained an edge because their seeds, protected by tough coats and nutrient stores, could survive dry spells and sprout when rains returned. Wind-borne pollen freed them from the need for standing water, and waxy leaves reduced water loss, making them ideal for deserts and dry forests. One of the most widespread Permian plants was Glossopteris, a seed fern whose broad, tongue-shaped leaves blanketed the southern part of Pangea, covering areas that today are South America, Africa, India, Antarctica, and Australia. Fossils of Glossopteris forests provided crucial evidence for Alfred Wegener's continental drift theory, helping scientists grasp how Pangea came to be. These forests offered shelter, food, and nesting sites for many herbivores that fed on leaves and seeds. The Permian's animal life was equally remarkable. Dominating the land were synapsids, early relatives of mammals, setting the stage for the ecosystems that would later be reshaped by the Permian's final, cataclysmic event, the greatest mass extinction in Earth's history, which wiped out most species and cleared the way for the age of dinosaurs. They weren't reptiles as we understand them today, but they also hadn't become mammals yet. From this intermediate group, mammals eventually emerged, so scientists often call them beast-like reptiles. In the early Permian, the landscape was dominated by pelycosaurs, the best known of which is Dimetrodon, with its large sail on the back. The sail may have helped the animal warm under the morning sun or cool during the midday heat. Pelycosaurs came in many shapes and sizes, from big predators to tiny insect hunters. Later, they gave way to a more advanced line of synapsids, therapsids. These creatures possessed stronger jaws, sharper teeth, and a more efficient way of moving on land. Some of their body features and behaviors already resembled those of modern mammals. Among therapsids, the dinocephalians included the largest animals of their time. This group contained peaceful herbivores with thick skulls, such as Estaminasuchus, which bore odd horn-like projections on its head, as well as fierce predators adapted for hunting. Their fossils appear in southern Africa and Russia, showing how widely Pangea was spread. Another major clade, the Dicynodonts, were tusked herbivores that ranged from dog-sized forms the size of a segamot. They had a beak for cutting vegetation and two prominent tusks, hence the name Dicynodont, meaning two canine teeth. One of the most successful members was Lystrosaurus, whose remains have been found on every Gondwanan continent, including Antarctica, confirming the close connection of those lands back then. Its ability to burrow likely helped it survive droughts and hide from predators. The true terrors of the Permian were the gorgonopsids, saber-toothed hunters with massive jaws capable of tearing prey. They sat atop the food chain and often preyed on dicynodonts. While synapsids dominated, reptiles began to make their mark. Large armored parasaurs like Parasaurus roamed the ground, moving like slow tanks, somewhere between a pangolin and an armadillo. Smaller, agile reptiles scurried through the underbrush. In the late Permian, primitive archosauriforms, the ancestors of dinosaurs and crocodiles, appeared, though they remained modest in size and easily overlooked. Amphibians persisted, especially in wet habitats. Giant, frog-like creatures lived in rivers and lakes, and the air hummed with insects, cockroaches, early beetles, and other arthropods. The sheer size of Pangea reshaped climate and life. A single massive continent altered wind patterns and ocean currents, making the interior scorching and dry, while coastal zones stayed relatively moist. This pressure forced plants and animals to adapt to harsh conditions. With no oceans separating lands, species could spread far across the supercontinent. Animals like Lystrosaurus and plants such as Glossopteris colonized vast areas, leaving modern scientists clues about ancient continental connections. Finally, at the close of the Permian, about 252 million years ago, a catastrophic event triggered one of Earth's greatest mass extinctions. After a series of catastrophic events, massive volcanic eruptions, a rapid climate collapse, and other disturbances, about 90% of marine species and 70% of terrestrial species vanished. This extinction was the greatest loss of life recorded on Earth, yet it also cleared the way for new forms to arise. In the quiet that followed, life began to rebuild, and a new chapter was about to start: the age of the dinosaurs. When the continents merged into the supercontinent Pangea, a chain reaction reshaped the planet. The Great Union of Land, which lasted roughly from 299 to 252 million years ago, altered not only geography but also the way animals lived, how plants spread, and the paths evolution could take. By joining almost all of Earth's land into a single mass, the massive oceans no longer isolated populations. Species that had once been separated by seas could now move across vast distances. Animals roamed freely over land, while wind and water carried plant seeds far and wide. Scientists call the resulting loss of regional uniqueness reduced provincialism. On separated continents, organisms evolve independently, but on Pangea, many regions hosted the same or very similar species. Fossils of the plant Glossopteris and the herbivorous reptile Lystrosaurus, found today in South America, Africa, Antarctica, and India, illustrate how life could disperse across what are now oceans thousands of kilometers apart. Across Pangea's varied climate zones, similar plants and animals performed comparable roles, making ecosystems more alike than ever before. The supercontinent stretched from pole to pole, creating stark climatic contrasts. Its interior was dry, hot, and desert-like, while coastal margins experienced milder conditions and seasonal monsoons that brought heavy rains. To survive, life adapted. Gymnosperms with tough leaves and protected seeds thrived inland, whereas moisture-loving plants that once dominated swampy coal forests persisted only along wet coasts and in deep rift valleys. Animals also changed. Many Permian synapsids, ancestors of mammals, developed clever strategies to cope with aridity,
Some became burrowers, others switched to tougher, more abundant food sources. Because the climate zones spanned such a huge area, the same adaptations helped species survive across much of the supercontinent. Pangea became a massive migration highway. When a region became too dry, cold, or crowded, creatures could simply move to a more favorable spot, sometimes traveling thousands of kilometers in search of food, shelter, or mates. This newfound mobility let them escape harsh conditions and explore new habitats, but it also intensified competition wherever different lineages met. Predators could roam far in search of prey, forcing their victims to keep moving to avoid attack.
With the continents welded into a single super landmass, ecosystems stretched across an entire continent, and the usual geographic barriers that spark new species were scarce. Rivers and mountain ranges existed, but they rarely split populations for long, so organisms stayed connected over great distances and seldom evolved in isolation. Consequently, global biodiversity on Pangea was lower than it later became on separated continents. Many species were widespread, yet overall variety was poorer and ecosystems more uniform. The vast, accessible land spurred a rapid expansion in size and complexity of terrestrial ecosystems, shifting the cradle of life from the oceans to the continents. During the Permian, a multitude of new forms appeared, most notably the therapsids, often called mammal-like reptiles, that thrived in Pangea's dry, seasonal landscapes. At the same time, gymnospermous cone-bearing plants, including early relatives of pines and cycads, spread across deserts and plains, turning barren expanses into active habitats. Marine life remained abundant, but evolutionary focus had clearly moved onto the continents. Ironically, the same connectivity that allowed species to disperse widely also made them vulnerable to global catastrophes. With ecosystems linked, a single disaster could affect the whole world. That is exactly what happened at the close of the Permian, about 252 million years ago. Massive eruptions in what is now Siberia created the Siberian traps, spewing enormous quantities of carbon dioxide into the atmosphere. The planet likely heated sharply, turning large regions hot and dry. Because Pangea offered few isolated refuges, organisms had nowhere to flee the lethal climate shift. This chain of events drove the Permian-Triassic extinction, the most devastating loss in Earth's history, eliminating roughly 90% of marine species and about 70% of terrestrial vertebrates. The story of life on Pangea illustrates a paradox. The supercontinent fostered unprecedented dispersal, the rise of new terrestrial ecosystems, and adaptations to harsh, arid conditions. Yet its very unity rendered it exquisitely susceptible to planet-wide calamities. The slow dance of tectonic plates that assembled Pangea reshaped the world in both magnificent and terrifying ways, turning the supercontinent into a stage for evolutionary triumphs and, ultimately, massive loss. It wasn't a local disaster like a volcanic eruption or a single region hurricane. The whole planet was hit by a massive crisis that wiped out roughly 90% of marine species and about 70% of land animals. This catastrophic episode occurred around 252 million years ago and is known to scientists as the Permian-Triassic extinction, often called the Great Dying. In the entire 4.5 billion year history of Earth, it remains the most devastating event. It was as if life had to squeeze through a narrow doorway. Many species failed to pass, and the survivors needed millions of years to recover. Before the collapse, the world looked nothing like today. All continents were fused into the supercontinent Pangea, stretching almost from the North Pole to the South Pole. This shape created a climate and ocean circulation very different from the modern ones. The interior of Pangea, far from any ocean, was a dry, harsh desert with rare rain and extreme temperature swings. Coastal zones were milder, sometimes tropical, with alternating wet and dry seasons reminiscent of today's monsoons. Despite these hardships, life thrived. The oceans teemed with an incredible variety of organisms, especially invertebrates such as ammonoids, brachiopods, trilobites, and colorful coral reefs. On land, synapsids, early relatives of mammals, ruled. Among them were large predatory gorgonopsians with saber-like teeth, and more peaceful herbivorous dicynodonts with beaks and tusks. One of the most common creatures was the small, leaf-eating therocephalian known as Lystrosaurus, which would soon face the looming apocalypse. Forests of conifers, seed ferns, and true ferns covered much of the continent, forming lush carpets that supported complex food webs. The world may not have been as bright or bustling as today, but it pulsed with life. The ultimate trigger of the extinction is thought to be a colossal series of volcanic eruptions in what is now Siberia, northern Asia. This was not a single volcano, but a massive flood basalt province where lava poured from gigantic fissures for millions of years, perhaps even a full million years. The eruptions blasted out lava through deep, 100-kilometer-long cracks, creating layers of black basalt up to thousands of meters thick. Scientists estimate that millions of cubic kilometers of lava were released, enough to blanket entire continents. The danger came not only from the lava, but also from the enormous volumes of gases it spewed into the atmosphere, chiefly carbon dioxide and sulfur gases. Sulfur gases can cool the planet by reflecting sunlight, while carbon dioxide traps heat. Over time, the warming effect dominated, turning the Earth into a scorching greenhouse. Moreover, the lava cut through layers of coal, oil, and salt, releasing additional toxic substances into the environment. The eruption released a mix of gases, sulfur compounds, methane, and chlorine and fluorine-bearing substances that could harm life in other ways. Together, they triggered an atmospheric disaster unlike anything Earth had seen before. At first, the massive sulfur outflow likely caused a brief volcanic winter, cooling the planet for a short spell. That chill faded quickly, and the relentless flood of carbon dioxide and methane drove temperatures upward at a frightening pace. In a geologically brief interval, the global temperature could have risen by more than 10 degrees Celsius, enough to turn forests into deserts and make the tropics nearly uninhabitable. The rapid warming left plants and animals no time to adapt. Forests withered, seed production halted, and vast tracts of land cracked and dried. Herbivores that depended on the dying vegetation vanished, followed shortly by the predators that fed on them. The entire food chain began to collapse. The oceans suffered even worse changes. As the water warmed, it held less dissolved oxygen, a vital resource for marine life. Oxygen levels fell, expanding so-called dead zones, while the seas simultaneously absorbed huge amounts of carbon dioxide and grew more acidic. The acidity made it nearly impossible for corals, mollusks, and plankton to build their calcium-rich shells. Without these tiny, essential organisms, marine ecosystems started to crumble from the bottom up. Increasing acidity and dwindling oxygen killed off more and more sea life, turning once vibrant communities into hot, acidic, almost lifeless expanses. The planet emerged from the event scarred and silent,
Forests thinned, oceans grew quiet. Life did not disappear entirely, but it was almost wiped out. It took millions of years for terrestrial ecosystems to recover and for new species to fill the vacant niches. Yet some resilient creatures survived. A small, hardy lizard, Zavra, managed to endure and spread across the continents.
Over time, evolution gave rise to the age of dinosaurs, far later in Earth's history. Imagine the ancient seas turning into vast, lifeless basins of poisonous water. As the planet heated, surface waters, once rich in oxygen, stopped mixing with colder depths, causing the oceans to stratify like a layered cake. Oxygen remained only at the top, while the deep layers became suffocating voids. Anoxic zones rose toward the shallows, turning thriving habitats into silent graveyards. Fish, corals, mollusks, and countless other marine residents died in massive numbers. In the oxygen-poor waters, unusual green sulfur bacteria, organisms that do not need oxygen, began to proliferate, further reshaping the marine environment. These tiny microbes released hydrogen sulfide, a poisonous gas that smelled like rotten eggs. As it built up in the seas, a new nightmare emerged: euxinia, a condition where water is deprived of oxygen and saturated with the toxic gas. The oceans turned from life-supporting to lethal. Black shales, rich in organic matter and sulfur, now found worldwide, record this disaster, preserving the memory of oceans that darkened, stank, and became deadly for almost all marine life. The fallout was catastrophic. Tiny plankton vanished, coral reefs collapsed, giant fish died, and even top predators perished. Some creatures were poisoned by the hydrogen sulfide, others simply suffocated. The thermocline, the invisible boundary separating warm surface waters from colder depths, rose, bringing oxygen-free, toxic water up to the surface and turning formerly safe habitats into death zones. Marine ecosystems that had flourished for millions of years were wiped out almost instantly. The crisis deepened when much of the sulfide escaped into the atmosphere, contaminating terrestrial animals and damaging the ozone layer that shields the planet from harmful ultraviolet radiation. With a weakened ozone shield, sunlight became lethal, scorching plants and animals and likely contributing to a massive die-off on land. Thus began a vicious chain reaction. Poisoned oceans harmed the sky, and the altered sky returned even greater devastation to the surface. At the heart of this cascade were the Siberian Traps, an immense region of present-day Russia where, about 252 million years ago, colossal eruptions spewed lava and gases for nearly 1 million years, releasing enormous amounts of carbon dioxide. The planet warmed, melting methane clathrates buried deep under the seafloor and in permafrost, releasing methane, a greenhouse gas far more potent than carbon dioxide. This additional methane accelerated warming, feeding the fire like extra fuel. Some scientists argue that widespread fires, sparked by drought and atmospheric changes, added even more carbon to the air. Ocean currents shifted, making oxygen distribution even harder. Each disaster amplified the others: heating oceans, lethal gases, suffocating life, and a poisoned sky locked the Earth in a deadly feedback loop. The destruction reached a scale never seen before or since. Roughly 90% of marine species vanished, and about 70% of terrestrial vertebrates were lost. Entire ancient groups that had survived for hundreds of millions of years disappeared, including the famous trilobites from the Cambrian, the blastoids related to sea lilies, many brachiopods, crinoids, and ammonoids, which survived only in a few remnants.
On land, giant predators such as gorgonopsids were wiped out, leaving only a few hardy survivors like the pig-sized, reptile-like Dicynodont Lystrosaurus. Even the early synapsids that would have given rise to mammals were largely exterminated. The whole web of life collapsed. Scientists described the event as selective extinction. Only organisms that could tolerate scorching heat, low oxygen, or acidic waters survived, while the majority perished. The few that made it through did so thanks to luck, hard-won endurance, or special adaptations. When the worst of the crisis passed, the planet fell into a deep silence that marks the early Triassic, often called the dead zone. Only a handful of robust species remained, and most surviving animals were tiny, a phenomenon known as dwarfism because large forms could not withstand the harsh conditions. A few disaster taxa came to dominate the empty ecosystems. Among them was a leaf-eating theropod that could live where almost nothing else could. Life's recovery stretched over millions of years, and the world that rose from the ashes was unmistakably different. The mass extinction cleared countless ecological niches, leaving vacant roles for newly evolving organisms. As these gaps filled, dinosaurs eventually rose to prominence, followed much later by mammals. In this way, the Great Die-Off sowed the foundations of the modern biosphere.
Researchers continue to probe the catastrophe with powerful instruments, dissecting ancient sedimentary rocks for chemical clues. They match the timing of volcanic eruptions, climate shifts, and oceanic oxygen levels, constructing intricate models of the event's progression. While details are still debated, most agree that the Siberian Trap's eruptions ignited the first spark of a global disaster. The episode serves as a stark reminder of the tight coupling between life and the planet, and of how quickly equilibrium can collapse. 252 million years ago, poisoned oceans and lethal gases threatened to erase life entirely. After a prolonged, painful struggle, a new, smaller, more modest biosphere emerged, ready to write a fresh chapter. Picture a world slowly rising from the ash of its greatest biological calamity. That was Earth at the dawn of the Triassic, a period that began roughly 252 million years ago and ended about 201 million years ago. The early Triassic followed a massive extinction that wiped out most marine organisms and countless terrestrial species. It began in an almost empty world and concluded with another, less catastrophic, but still significant extinction. Between these two crises, life returned in slow, often bizarre forms. Ecosystems rebuilt themselves, plants and animals explored new shapes, and vacant niches were gradually occupied. The first dinosaurs and the earliest ancestors of mammals appeared during this time, their competition laying the groundwork for later evolutionary revolutions. Survivors found themselves with few rivals and abundant open spaces, allowing experimentation and diversification. The Triassic planet looked very different from today. Almost all land was fused into the colossal supercontinent Pangea, stretching from pole to pole and encircled by the vast global ocean Panthalassa. The interior of the supercontinent was far from the cooling influence of the oceans, so the land's core was scorching hot and bone dry. Under an unrelenting sun, vast deserts stretched across the continent. Yet the coasts weren't always parched. Rock layers and sediment show that some shoreline regions experienced powerful seasonal monsoons that brought brief, heavy downpours. Throughout the Triassic, the global climate stayed very warm. Polar ice caps were absent, and the seas remained relatively warm and sluggish, still healing from the earlier mass extinction. Because cold currents were missing,
Ocean water held less oxygen, which made the recovery of marine life difficult. After the devastation, the dry land was almost barren, populated only by a few tough, fast-growing plants, such as a thin-stalked spore fern. Over time, vegetation rebounded. By the Middle and Late Triassic, forests of tall conifers and palm-like sago and ginkgo trees covered the landscape, providing shelter and food for fungi. These woodlands laid the groundwork for more intricate food webs and stable ecosystems. In the immediate aftermath of the Permian extinction, ecosystems were simple and dominated by a handful of survivors. Paleontologists refer to these hardy survivors as toxons. One such survivor was a pig-sized dicynodont with a short-tusked, bulldog-like face, often called the Triassic arc. Its low food needs, ability to dig burrows, and tolerance of low oxygen conditions allowed it to spread across what is now Antarctica, South Africa, India, and China, areas that were then joined in southern Pangea. As the planet healed, new animal groups appeared, most notably the archosauromorphs, the ancestors of crocodiles and dinosaurs. Early archosauromorphs looked like elongated lizards. Many were small and swift, equipped with more efficient lungs, lighter bodies, and stronger, lower-energy movements. These traits gave them a decisive edge as ecosystems grew more complex. Around 230 million years ago, the first true dinosaurs emerged. They were not giants at first. Early dinosaurs were modest in size, walked on two legs, and were built for speed. Species such as Eoraptor, Herrerasaurus, and Staurikosaurus, known from Argentine rock formations, were agile hunters about the size of a modern human. Their sharp teeth indicate a carnivorous diet, hunting small prey or scavenging carcasses. Early dinosaurs stood upright and moved quickly, their front limbs probably used for grasping. Yet they had not yet become the dominant land animals. Other archosaur relatives still ruled the continents. While dinosaurs were gaining strength, the land was ruled by pseudosuchians, ancient cousins of crocodiles. This group included a variety of powerful forms. Phytosaurs looked like crocodiles but had nostrils high on the head and lived in water. They were herbivores protected by heavy armor that made them resemble tanks. Rauisuchians were fierce terrestrial predators, giant bipedal crocodile-like hunters that sat at the top of the food chain while early dinosaurs lingered in the shadows. At the same time, another lineage was undergoing a quiet revolution: the cynodonts, ancestors of mammals. In the Permian, synapsids dominated, but the Great Extinction wiped out most of them, leaving only a few survivors. Those survivors began to change in subtle but crucial ways. Their teeth diversified, sharp incisors, pointed canines, and grinding molars, allowing more efficient chewing, which was vital for animals with high energy needs. A secondary palate formed, separating the breathing passage from the mouth so they could chew and breathe at the same time. The lower jaw remodeled. Some bones shrank and later became part of the middle ear, a hallmark of true mammals. Fossils such as Triconodon and Cynognathus illustrate this transition. Although they still resembled reptiles, they increasingly looked and behaved like mammals. Some researchers think they were warm-blooded and may have possessed whiskers and fur, giving them an edge in cold or unpredictable climates. The Triassic was a period of trial, error, destruction, and renewal. After the worst extinction, the planet healed, and new, powerful lineages prepared to shape the future. Dinosaurs began their long march toward dominance, while mammal ancestors quietly refined traits that would one day lead to us. The supercontinent split under a blazing sun, and strange reptiles ruled both land and sea. This era acted as an evolutionary laboratory, forging the future rulers of Earth. By the end of the Triassic, about 201 million years ago, millions of years of gradual change gave rise to the first true mammals. These pioneers were tiny, often no larger than a modern shrew. They likely spent most of their lives in darkness and were nocturnal, a lifestyle that shielded them from large, dangerous reptiles that roamed the land by day. Small size and night activity were not accidental. They were essential survival strategies. By being active at night and remaining unseen, these diminutive mammals avoided direct competition with the massive archosaurs that ruled daylight. They did not chase the same prey. Instead, they carved out a quiet niche, hunting insects and other small invertebrates that big reptiles ignored or could not catch.
Living alongside towering dinosaurs and fearsome predators, the tiny mammals did more than hide. They followed their own unique evolutionary path, laying the groundwork for the mammals we know today. At that moment, the traits that would later define all mammals first appeared. Warm-bloodedness, the ability to nurse offspring with milk, sharp hearing, and a brain large for the body size. These features didn't yet make mammals dominant, but they laid the groundwork for the greatness that would emerge long after the dinosaurs vanished. The Triassic stretched from roughly 252 to 201 million years ago. Earth was still healing from the greatest mass extinction in its history, and life was gradually refilling the empty niches. Most of the continents were ruled by pseudosuchians, distant relatives of today's crocodiles, whose many shapes and sizes kept them at the top of the food chain for tens of millions of years. Freshwater habitats teemed with huge phytosaurs, crocodile-like reptiles that dominated the water food web. On land, heavily armored herbivores called atasaurs moved like living tanks, while swift, powerful hunters such as the Rauisuchian Postosuchus roamed the plains. These predators often far outsize early dinosaurs, which at the time were small, inconspicuous survivors, likely scavenging or feeding on modest prey. Around 200 million years ago, at the close of the Triassic, a sudden shift occurred. A new mass extinction, known as the Triassic-Jurassic event, swept the planet. Although less catastrophic than the earlier Permian crisis, it was still profound. Scientists link it to a series of colossal volcanic eruptions triggered by the slow breakup of the supercontinent Pangea. The eruptions created the Central Atlantic Magmatic Province, a vast area of volcanic rock now found in present-day North and South America and Africa. Enormous volumes of carbon dioxide and sulfur gases poured into the atmosphere, prompting rapid global warming, ocean acidification, and a cascade of ecological upheavals. The dominant Triassic reptiles, pseudosuchians, atasaurs, phytosaurs, and Rauisuchians, suffered the brunt of this disaster, with many vanishing entirely. Dinosaurs, for reasons still debated, managed to persist. Their possible advantages included more efficient movement, a flexible diet, or sheer luck. With their rivals gone, dinosaurs began to grow larger, occupy new ecological roles, and diversify dramatically. Within a few million years of the extinction, in the early Jurassic, the variety of dinosaurs surged. Gigantic sauropods with necks as long as a bus, towering herbivores, and fierce theropods that would later give rise to giants like Tyrannosaurus rex. Thus, the true age of dinosaurs truly began. But its roots lie in the Triassic, a period that was not only about survival, but also a pivotal turning point in the history of life. It was a time when mammals, dinosaurs, and many other groups began their long evolutionary journeys. Fossil discoveries from around the world have greatly expanded our knowledge of the Triassic. In Argentina's Chugualasta Formation, richly fossil-laden rocks have yielded some of the best-preserved early dinosaurs, such as Gyroraptor and Eoraptor. In southern Africa, scientists have found fossils of ancient synapsids, including cynodonts, mammal relatives that illustrate the gradual shift from reptile-like ancestors to true mammals. In North America, the Chinle Formation has acted as a treasure trove of Triassic reptiles, revealing a strange and diverse world that lived alongside the first dinosaurs. Every fossil, whether a single tooth or a whole skeleton, adds a new piece to the mosaic of this remarkable era. Researchers constantly re-examine old data and employ new tools, computer tomography, digital modeling, and other technologies to uncover ever more detail. The Triassic demonstrates life's extraordinary ability to recover, adapt, and innovate after Earth's greatest catastrophes. Tiny mammals took their first steps, while dinosaurs began a long ascent toward dominance that would shape life for the next 135 million years. Imagine a landmass so vast that one could theoretically travel from the South Pole to the North Pole without ever crossing an ocean. That was Pangea, the gigantic supercontinent that dominated Earth from the late Paleozoic to the early Mesozoic for hundreds of millions of years. It was not merely a collection of squeezed-together continents, but almost the entire planet's land surface united in a single block. The immense size of Pangea reshaped the planet's appearance and its climate. Today, we live on a world of scattered continents and oceans, each with its own weather patterns. In Pangea's age, everything operated on a far larger scale. The supercontinent generated a massive, harsh climate system, unlike anything we know. Coastal margins experienced milder, wetter conditions, while the interior remained scorching, dry, and unforgiving. Studying Pangea's climate shows how the arrangement of land and sea governs winds, precipitation, ocean currents, and even life itself. The most extreme climate features appeared at the continent's core. Picture a land so broad that moist oceanic winds, after traveling thousands of kilometers, lost all their moisture long before reaching the interior. By the time they arrived, the air was dry and unable to bring rain. Consequently, Pangea's heart suffered chronic drought, not a typical desert, but a super desert, covering areas that today correspond to North America, South America, and Africa. Vast sand seas, ergs, stretched across the land, with wind endlessly reshaping towering dunes. Between the dunes lay dry salt flats and seasonal lakes that briefly filled after rare rains, only to evaporate quickly under the scorching sun, leaving thick crusts of salt and minerals. The interior air of Pangea was dusty and often reddish, tinted by tiny iron-rich particles lifted from oxidized soils. Red rock layers, gypsum, and rock salt deposits found on many modern continents point to a period of severe drought and heat. Plants and animals needed special toughness. Early conifers and sphenophytes grew waxy leaves and deep roots to retain moisture and tap hidden groundwater, while nearby creatures also had to endure chronic water scarcity. Because the supercontinent was extremely wide, its center lay far from any ocean, preventing moist air from reaching it and creating a harsh, closed climate. In contrast, The margins bordering Panthalassa and the Great Tethys Ocean enjoyed milder conditions, receiving more humidity, regular rain, and smaller temperature swings, which allowed lush forests, rivers, and swamps to thrive, evidence of which survives today. Massive coal seams formed during the Carboniferous and Permian periods, about 350 to 250 million years ago, originated from vast tropical forests that grew in warm, wet lowlands around Pangea's edges. The land was carpeted with lycophytes, ferns, and horsetails that soaked up rain and later turned into the coal we now use. Nearby seas teemed with life. Fossils of marine animals, coral reefs, and shell beds along ancient shores testify to thriving ecosystems.
Though the exact routes of ancient ocean currents remain under study, they likely carried warm, moist air across the supercontinent, making the coasts far more hospitable than the arid interior. Thus, during Pangea's age, the Earth was a realm of extremes, a scorching desert core surrounded by verdant, wet margins shaped by the interaction of land, sea, and air. This illustrates how continental placement governs climate and life. One striking result of Pangea's size was a gigantic seasonal weather system, a supercontinental monsoon. Modern monsoons arise because land and ocean heat and cool at different rates. With Pangea's immense land area, the effect was amplified. In summer, the interior heated rapidly while the surrounding ocean stayed cooler, creating a large pressure difference, low over the hot land, high over the sea, drawing massive, moist air toward the continent. During the time of Pangea, monsoon rains covered the supercontinent on a scale far larger than anything we see today. Moist, wind-driven storms brought nearly non-stop summer downpours, especially along the coasts. Rivers burst their banks, flooding whole regions, while even far inland plains received enough rain to turn dry ground into blooming green fields. When winter arrived, the situation reversed. Land cooled much faster than the ocean, creating dense, heavy air above the continent and a strong, high-pressure zone, while the sea retained relatively lower pressure. Cold, dry winds then swept from the interior toward the ocean, ushering a harsh, arid season that spread across much of Pangea. These abrupt shifts between wet and dry periods profoundly reshaped the landscape. The alternating cycles left a clear imprint in the geological record. Rivers deposited successive layers of coarse and fine sediments known as rhythmites, marking each seasonal change. Ancient paleosols preserve evidence of repeated wet and dry phases, and fossilized plant remains reveal how vegetation responded. Many species evolved strategies to endure the dry months and then explode in growth once the rains returned, illustrating life's adaptation to extreme climate swings. Because Pangea was so immense, the supermonsoon system acted like a global climate engine, influencing weather far beyond a single region and operating far more powerfully than today's monsoons. Around the same era, the planet entered a major glaciation often called the Permo-Carboniferous Ice Age.
This was not a localized cooling, but a worldwide event that spread thick ice sheets across vast territories. It began more than 300 million years ago, when much of the southern supercontinent Gondwana, now comprising Africa, South America, Antarctica, Australia, and India, drifted over the South Pole. Positioned over the coldest part of the globe, the land continuously accumulated snow that never melted, even in summer, eventually forming massive glaciers and ice caps. A crucial driver of this cooling was a sharp decline in atmospheric carbon dioxide. During the Carboniferous period, expansive forests produced thick coal deposits. When these plants died, their carbon became buried, pulling large amounts of CO2 out of the atmosphere. The resulting greenhouse gas drop cooled the climate and allowed ice to spread further. Continental movements also reshaped ocean currents, closing or narrowing some sea routes and redistributing planetary heat, which further promoted polar ice growth. Geologists find evidence of this ancient glaciation across all southern continents. Tillite deposits composed of glacial debris, striated rock surfaces, and stones polished by the slow advance of enormous ice sheets. These remnants testify to a time when both extreme monsoons and a planet-wide ice age shaped the early Earth. Evidence for the ancient world comes from glacially carved troughs, coarse gravel beds, and huge rocks that fell into fine-grained sediments and later became icebergs. For millions of years, the supercontinent Pangea drifted slowly northward. Its icy shields melted, and during the Triassic and Jurassic periods, the planet entered a warmer phase. This shows how intricate Earth's climate is, driven by continental motions, atmospheric gas composition, and even the planet's orbit around the Sun. Pangea reshaped not only land and ice, but also oceanic and atmospheric behavior on a global scale. A massive continent was encircled by the endless ocean Panthalassa, unlike today's seas divided by continents. Panthalassa allowed colossal currents to sweep freely around the globe, perhaps simplifying deep water circulation and making some regions more stable. Along Pangea's eastern edge lay the Tethys Ocean, a warm, shallow sea that acted as a huge heat reservoir. It helped regulate temperature and exchanged water with the larger Panthalassa, creating powerful currents that have no modern counterpart. The basic atmospheric structure, rising and sinking cells known today as Hadley, Ferrel, and Polar, remained, but the sheer size of Pangea amplified them. Vast heating and cooling of the land intensified pressure belts, spawning gigantic supermonsoons. With fewer mountain ranges, winds faced fewer obstacles and could travel great distances, so a climate shift in one part could ripple thousands of kilometers away through a teleconnection of weather patterns. Moisture from Panthalassa highlighted the contrast between lush, green coasts and a dry, often harsh interior, especially in winter. The climate featured scorching summers, freezing winters, fierce monsoons, and occasional icy spells, shaping life dramatically. Plants and animals in the arid interior adapted to water scarcity, while coastal zones supported rich ecosystems. Because oceans did not divide the continent, species dispersed widely, resulting in lower regional diversity than today. Like earlier supercontinents, Pangea could not endure forever. Deep-seated tectonic forces began to pull it apart near the end of the Triassic, about 200 million years ago. The breakup unfolded gradually over tens of millions of years, with pressure building beneath the crust until the land bulged outward like a giant inhalation, marking the slow disintegration of the once vast supercontinent. Finally, the crust began to split, carving huge rift valleys, deep, long scars across the ancient supercontinent. Understanding why such massive land masses fell apart explains today's continents and oceans. Deep beneath the planet, the mantle circulates in slow, swirling currents of hot rock, much like water boiling in a pot. These flows drive continental drift. When a supercontinent covers much of the Earth, it acts like a thick blanket, trapping heat produced by the slow decay of radioactive elements deep below. Over millions of years, that heat builds up, making the underlying mantle hotter and lighter. It rises, pushes the crust upward, and stretches it until it cracks. Another key factor is a mantle plume, a hot column of rock rising from near the core mantle boundary.
When it reaches the base of the crust, it creates a volcanic hotspot, adding both heat and pressure that further weakens the crust. The Central Atlantic Magmatic Province, formed about 200 million years ago as the Atlantic opened, exemplifies such plume activity.
Its massive lava flows spread over what are now North America, South America, Africa, and Europe, indicating one or several huge plumes that helped thin the supercontinent's crust and start its breakup. Early in the breakup, internal mantle forces dominated, inflating the land and generating the first rifts. Later, plate motions such as subduction and seafloor spreading took over. Rift valleys were the first visible sign that the supercontinent Pangea was beginning to fall apart. As the crust cracked and thinned, the pressure on the mantle dropped, allowing rock to melt and form magma. This magma surged upward through the fissures, triggering massive volcanic eruptions that spewed thick lava flows and basaltic layers, blanketing vast areas with dark, stone-filled plains. The ancient lava fields that can still be seen today, such as those at Camp, show how much heat rose from the Earth's interior and serve as a clear marker of a major geological upheaval. The earliest rifts later became the birthplaces of today's oceans. The most important was the Central Atlantic Rift System, where the Atlantic Ocean first opened. The rift began between what are now North America and Africa, then pushed southward, separating South America from Africa and creating the South Atlantic Rift. At first, the rift consisted of a chain of isolated, narrow basins stretching for hundreds of kilometers. Over millions of years, those basins merged and widened, turning into larger depressions. Some of these ancient basins are still exposed. For example, the Newark supergroup on the U.S. East Coast records river and lake sediments mixed with volcanic ash that tell the story of the crust's split. A similar process farther south eventually pulled South America away from Africa. Today's analog is the East African Rift, where the continent is literally being torn apart. In East Africa, one can see uplifted blocks, deep faults that form grabens and horsts, a string of active volcanoes, and long lakes that fill the valleys. This living laboratory demonstrates that the forces that once ripped Pangea apart are still at work. Not every rift matures into an ocean. Some start to split the crust, but stall before full separation. These are called failed rifts or olacogens. They appear as forgotten scars where the land began to break but never completed the division. Over time, thick sediment piles up in these zones, and renewed tectonic stress can reactivate them. Failed rifts can still be significant. In West Africa, a dead branch of the South Atlantic Rift remains, and in the central United States, the Rilfud Rift is a relic of a split linked to the ancient Jape Ocean that existed long before Pangea. Such structures act as time capsules, preserving layers of Earth's past and often holding valuable oil and gas deposits. Geologists study the breakup of Pangea through a variety of records scattered across the planet. Among the clearest evidence are the deep cracks and valleys that formed as the crust stretched. Those rift valleys deepened into large basins that collected silt, sand, gravel, and entire river-lake systems. Over time, the basins filled with sandstones, clay shales, conglomerates, and characteristic red-tinged strata, providing a detailed archive of the planet's early tectonic drama. The reddish rocks you see are stained by iron-rich minerals that have oxidized in the open air, and their color tells geologists a lot about past conditions. During the era when the supercontinent was breaking apart, the climate was often hot and dry, much like today's deserts. In partially closed rift valleys, seawater would occasionally flood in and then evaporate, leaving thick deposits of evaporites. layers of halite, rock salt, and gypsum, the soft mineral still used for plaster. These minerals formed in repeated cycles of flooding and drying, like a salty pond that keeps evaporating under the sun. Such salt layers are crucial in oil and gas exploration because they can act as seals that trap hydrocarbons. In the wetter parts of the rift system, or during more humid periods, swamps and lush vegetation developed. Over time, those swamps could turn into coal beds, showing that not every rift valley was a barren desert. Some were green and teeming with life. The most striking evidence of Pangea's breakup comes from magmatic rocks produced by mantle magma that rose as the crust stretched and thinned. Massive lava flows created vast fields of dark volcanic basalt, the best known being the Central Atlantic Magmatic Province, the Parana et Endeca Province spanning South America and Africa, and the Karoo Province in southern Africa. When these flows cooled, they sometimes formed the famous hexagonal columnar joints. Magma also intruded underground, forming dikes, sills, and horizontal sheets, essentially a frozen plumbing system within the rift zone. By analyzing the chemistry of these volcanic rocks, scientists pinpoint the magma's source, often directly in the mantle, where melt is drawn up by crustal extension. On the structural side, normal faults, places where one side drops as the crust pulls apart, are clear markers of rift formation. They appear on geological maps and are highlighted by seismic imaging, which also reveals classic Graben-Horst patterns of down-thrown and uplifted blocks. Even though many ancient rift valleys are buried beneath kilometers of younger sediment, methods such as gravity surveys and seismic reflection still detect the thinned crust. Paleomagnetism adds another line of proof. As volcanic rocks cool, magnetic minerals align with Earth's magnetic field of the time. Studying these orientations in rift zones allows geologists to date the rifting and calculate continental spreading rates. When rifting gave way to oceanic crust formation, the magnetic record was preserved in symmetric stripes on either side of mid-ocean ridges, like a barcode that precisely marks the opening of the ocean and the split of the continents. Even the oldest rocks record the story of Pangea's breakup. They don't capture rift formation directly, but they provide strong indirect clues. Fossils of the modest reptile Lystrosaurus, about the size of a pig, have been found in Africa, Antarctica, and India, regions now separated by oceans. This shows that those continents were once united in the massive supercontinent Pangea. When the land masses began to split, the species followed different paths and evolved independently, creating a biological timeline that matches the geological record. Riftogenesis reaches its final stage when the continental crust fully fractures and magma rises from the mantle, not just as cracks, but to create new oceanic crust. A new ocean basin starts to form. Today's Red Sea illustrates this process, a long, narrow stretch of water between Africa and the Arabian Peninsula, where the crust is being pulled apart and fresh seafloor is generated, just as it did at the onset of Pangea's breakup. The disintegration of Pangea was one of the planet's most powerful and slowest transformations. It did not happen in an instant. It unfolded over millions of years. First, the crust stretched and cracked, forming valleys that filled with rivers and lakes, massive lava flows, and slowly accumulating thick layers of salt and coal. The era was marked by tension, fire, and constant change. Now the evidence is everywhere: enfolded rocks, fault lines, volcanic scars, and matching fossils on opposite sides of oceans. These geological marks are the fingerprints of Pangea's gradual, dramatic split and remind us that Earth's surface never stays still. Continents continue to drift, fracture, and occasionally reunite in an endless cycle, preserving the memory of Pangea deep within the planet. Imagine Earth not as a silent, unmoving stone, but as a living, breathing giant with a fiery heart. Beneath our feet, enormous forces constantly move and reshape the surface. For hundreds of millions of years, continents glide like slow-moving pieces of a mosaic. Sometimes they collide, forming supercontinents like Pangea. Other times they tear apart, spawning new oceans and reshaping the planet's face. What drives such massive, solid rock to move, split, and change so dramatically? Most scientists point to deep inside processes, mantle plumes and hotspots, that act like giant underground furnaces. These features lift huge amounts of heat from the depths, offering vital clues about Earth's long-term motion. To grasp these hidden forces, we must look far beneath the surface, into the Earth's interior, where everything is far from calm. Between the solid crust and the molten outer core lies the mantle, a layer thousands of kilometers thick that behaves, over long periods, more like a thick, slow-moving liquid than a rigid stone. The mantle circulates by convection. Hot material rises from the bottom, while cooler material near the surface sinks, much like a pot of stew slowly simmering on a stove. Continuous mixing also occurs in the mantle, but it takes millions of years instead of minutes. Mantle plumes appear as massive columns of scorching rock that push upward through the slowly moving mantle. Most geologists agree that these plumes begin at a hidden boundary where the mantle meets the outer core, a zone about 3,000 kilometers beneath our feet, known as the D double prime layer. Temperatures there are comparable to the surface of the Sun, and in this furnace, some mantle material heats enough to become slightly less dense than its surroundings and start a slow rise, much like a hot air balloon lifting because the air inside is warmer than the air outside. A typical plume has a mushroom shape, a long, thin stem reaching up from deep earth, and the broad cap at the top that can be several hundred to more than 1,000 kilometers wide, spreading just beneath the surface. When the plume reaches the base of the rigid lithosphere, the crust and upper mantle, it pushes the whole lithospheric slab upward, forming a dome that may rise a few hundred meters or even over a kilometer. This uplift stretches the crust, thinning and weakening it like an overstretched rubber band, eventually causing it to crack and form narrow, deep rift valleys. The heat of the plume also melts mantle rock beneath the crust, creating vast pools of magma. Because magma is lighter than solid rock, it climbs through the fractures and erupts in colossal events far larger than ordinary volcanoes. These massive eruptions can blanket entire regions with lava and are recorded as large magmatic provinces. Ancient examples include the Deccan Traps of India and the Siberian Traps of Russia, each covering an area the size of a country and consisting of thick layers of solidified lava that testify to the power of deep earth processes. The entire sequence, deep heat inflating the surface, stretching and cracking the crust, and then flooding the area with lava, is a crucial mechanism in the breakup of continents. A rising plume weakens the crust from below, creates slopes that gravity pulls apart, and thins the lithosphere, making it easier to split. When the crust finally ruptures, two continental fragments can drift away, and a new oceanic basin forms between them. The disintegration of the ancient supercontinent Pangea, about 200 million years ago, is thought to have been triggered by such mantle plumes, which caused broad uplift and enormous volcanic eruptions. Classic lava flows built an extensive volcanic plateau. The internal heat and activity weakened the thick crust of the supercontinent, making it vulnerable to the stretching and compressing forces of plate tectonics. Eventually, the combination of internal heat and external stress exceeded the crust's strength. Cracks appeared, continents began to drift apart, and the once whole supercontinent started to break into the smaller continents we know today. In the most literal sense, fire deep within the Earth helped tear the supercontinent apart and continues to shape our planet. Hotspots are surface clues to far deeper, dramatic processes beneath our feet. When a plume of overheated material rises from the mantle and melts the rigid lithospheric layer above it, a long-lasting source of volcanic activity is created. Many hotspots, such as the famous one beneath the Hawaiian Islands, stay roughly fixed in the mantle while the surface, broken into moving plates, slides over them. As a plate slowly moves above a stationary hotspot, intense heat repeatedly pierces the moving crust, forming a chain of volcanoes. The youngest, most active volcano sits directly above the hotspot. Older volcanoes trail behind like a wake. Imagine a conveyor belt passing over a glowing lamp. The lamp stays still, but the belt receives a series of burnt marks. That is how volcanic island chains are formed. The tracks left by hotspots give scientists valuable information about both the origin of volcanoes and the motion of tectonic plates over millions of years. There is strong evidence that mantle plumes originate deep within the Earth, far below the zones where most volcanic activity occurs. How does volcanism reveal plate movement changes? The answer lies in the scale, style, and location of eruptions. Occasionally, massive eruptions cover vast areas with lava in just a few million years, a blink in geological time. These events, called flood basalt eruptions, are linked to large magmatic provinces. They are far more voluminous than the slow lava flows on oceanic ridges or the explosive cone volcanoes at subduction zones. Flood basalts point to an extraordinary process beneath the surface, a gigantic flow of hot magma rising directly from the mantle. Chemical analysis of lava also tells its origin. Many of these lavas are tholeiitic basalts, produced by melting deep mantle rock rather than shallow crust. This geochemical fingerprint helps differentiate deep mantle plumes from volcanism caused by crustal stretching, which typically yields silica-rich lava. One key clue is the location of huge eruptions. When they happen far from plate boundaries, in the interior of a continent, they strongly indicate a mantle plume's influence. Most volcanoes form at plate margins, where plates collide, separate, or slide past each other. Therefore, volcanism occurring in the middle of a tectonic plate usually signals that a massive, deep, hot plume has breached the surface, uplifted the crust, and split it apart. About 200 million years ago, the supercontinent Pangea began to fall apart. Enormous lava floods swept over the territories that would later become North and South America, Africa, and Europe, delivering a clear warning that the planet's interior was building pressure. The breakup starts when a rising mantle plume head pushes up against the lithosphere. The crust bows, stretches, and deep cracks, rift valleys appear. As the crust thins and heat accumulates,
huge volumes of magma break through, spreading outward as massive basaltic flows. That volcanic surge marks the point of no return. The weakened crust finally cracks, opening the way for new ocean basins. Often, this volcanic episode happens just before the seafloor begins to spread. A striking illustration is the Central Atlantic Magmatic Province, CAMP. Around 200 million years ago, along the future seams of the Atlantic, a gigantic lava eruption occurred. CAMP demonstrates the direct link between massive volcanism and the forces that split the ocean. Even after the continents split, mantle plumes and hotspots stay active. As tectonic plates move over them, they leave chains of volcanic islands like the Hawaiian archipelago. Each island or underwater mountain records a step in the plate's motion, acting as a geological map of Earth's slow drift. Mantle plumes transport enormous heat and melt toward the surface. That energy can lift, stretch, and eventually tear the crust apart. The formation of huge magmatic provinces, such as CAMP, unequivocally signals a major reshaping of the planet. Imagine the distant past, when almost all land was united in one colossal block stretching from the frozen South Pole to the icy North. It was a world of ancient deserts, scorching suns, and towering mountain ranges, now long eroded but once the foundation of the supercontinent that would give way to new oceans and a new chapter in Earth's ever-changing story. The Earth's crust once seemed solid, and the continents appeared locked together in an ancient unity. Beneath the surface, however, powerful forces were quietly building. Even the greatest structures are not eternal. The massive supercontinent Pangea was destined to break apart. Its slow, dramatic disintegration became one of the most remarkable geological events in the planet's history. It did not happen in a single night.
The process was long, chaotic, and fiery, and the first great chapter in this story was the birth of the Atlantic Ocean, sparked by one of the world's largest volcanic episodes, the formation of the Central Atlantic Magmatic Province, or CAMP. Before that fiery beginning, Pangea itself had to form. Over tens of millions of years, ancient land masses collided and fused, gradually assembling a single, enormous supercontinent. About 300 million years ago, these collisions finally united almost all of Earth's land. The creation of Pangea reshaped climate, ocean currents, and the course of evolution. Deep beneath its massive surface, heat constantly rose from the mantle, generating slow, thick currents that acted like a simmering soup in a pot. These currents built tension under the crust, pressing down on the land above. The first signs of change were subtle. Pangea did not explode or collapse suddenly. It began to stretch so gradually that a human lifetime would not reveal it. This early phase, called continental riftogenesis, resembled pulling a thick piece of dough. It lengthens, thins in the middle, and eventually tears. As the supercontinent stretched, the continental crust cracked, forming a mosaic of long fissures, lowered valleys, rifts, and grabens, blocks of land that sank between the breaks. These features turned into narrow basins that would become the earliest Atlantic Ocean. Rivers flowed into the deepening cracks, laying down layers of silt, sand, and other sediments that recorded the dramatic era. Then the true geological spectacle unfolded. A massive volcanic event transformed the slow rift into a full-scale breakup. The eruption of CAMP was not an ordinary volcano. It was one of the largest lava outpourings ever recorded. Occurring around 200 million years ago at the boundary between the Triassic and Jurassic periods, Camp's eruption coincided almost exactly with the onset of Pangea's split and the birth of the Atlantic. Lava from Camp spread across what are now North America, South America, Northwest Africa, and Southwest Europe, 4 continents still joined at the time. Scientists estimate that between 2 and 4 million cubic kilometers of magma were expelled, enough to bury entire regions under hundreds of meters of solid rock. This colossal eruption marked the decisive moment when the ancient supercontinent finally shattered, giving rise to the oceans and continents we know today. Recall the 1815 eruption of Tambora, the largest recorded volcanic event in human history. Now imagine that magnitude multiplied by thousands, perhaps tens of thousands. That was the primordial force we are describing. These eruptions did not arise from the tall, conical volcanoes familiar from movies. Instead, they erupted with an effusive character. Lava poured out in vast sheets, flooding entire landscapes and forming thick layers of dark basalt. In the resulting rock, scientists have identified a special type of volcanic material called talc-bearing basalt. It forms when mantle material melts deep within the earth and rises to the surface. This indicates that the eruptions were not merely superficial. They originated from profound depths, likely triggered by a massive mantle plume, a towering column of hot rock that ascended from the mantle, melting everything in its path. When this plume reached the base of the continental crust of Pangea, it caused extensive melting, uplift, and eventually colossal eruptions. Most of the basaltic flow was deposited over a relatively short geological interval, perhaps 1 to 5 million years. This intense activity coincided with the initial opening of the Atlantic, meaning the mantle plume did not merely coincide with Pangea's breakup, it helped drive it. The extreme heat and pressure of the plume weakened the already stretched, thinned crust, much like heating a cracked sheet of glass until it shatters. The crust split, the earth opened, and a new ocean basin, the modern Atlantic, was born. To grasp the Atlantic's origin, picture the proto-ocean. It was not the wide, deep sea we see today, but a narrow, elongated fissure, a newborn ocean. In its center, fresh oceanic crust formed from molten mantle material that cooled and solidified as the basin widened. As the continents drifted apart, the thick crust beneath them eventually fractured, allowing hot mantle to rise, melt under reduced pressure, and generate new crust along the rift. Thus, new oceans are created. The early Atlantic, or Proto-Atlantic, likely resembled today's Red Sea, a long, narrow waterway over hot crust with vigorous volcanic activity along its spine. The ocean did not appear instantly. It expanded gradually, beginning near the central rift and extending northward and southward over time. One of the earliest signs of this grand event were the massive eruptions of the Central Atlantic Magmatic Province, marking the first major split between what would become North America on one side and Africa and South America on the other. As the rift widened, oceanic crust continued to grow, shaping the Atlantic we know today. Along a growing crack, now called the Mid-Atlantic Ridge, fresh oceanic crust has been popping up continuously. This underwater mountain chain runs down the center of the Atlantic and still pushes the seafloor outward, pulling the continents apart. Geologists have gathered many clues that prove this. The clearest one is the pattern of magnetic stripes on the ocean floor. When new rock solidifies at the ridge, it locks in the direction of Earth's magnetic field at that moment. Because the field has flipped many times, alternating bands of normal and reversed magnetization appear on both sides of the ridge, like a perfect mirror image barcode. Those stripes tell exactly where, when, and how the seafloor was created. Additional evidence comes from the shape of the seabed, rift valleys where the crust is tearing, and from sediment layers that change from shallow water to deep water deposits as the basin deepened. The birth of the Atlantic was more than a geological event. It reshaped climate and life. Around 200 million years ago, the Central Atlantic magmatic province erupted, spewing massive amounts of carbon dioxide and sulfur gases. The carbon dioxide drove a long-term greenhouse warming and made the oceans more acidic, harming marine organisms. The sulfur aerosols briefly dimmed sunlight, cooling the planet, but after the short chill, the climate likely warmed even further. Many scientists link this dramatic upheaval to the Triassic-Jurassic extinction, one of the 5 greatest mass killings in Earth's history. The timing fits, and fragile ecosystems would have been vulnerable to such volcanic blows. Opening the new ocean also broke the once continuous global sea that surrounded Pangea, creating fresh currents that moved warm water in new ways and altered the climate. New coastlines and habitats appeared, setting the stage for divergent evolution of plants and animals on the separating continents, which today gives us the rich diversity we see. The ridge is still alive. It adds a few centimeters of new crust each year, steadily widening the Atlantic and shifting North America, South America, Europe, and Africa. The early Atlantic was not just a crack or a strip of water. It was the first sign that the great supercontinent was fragmenting, and the magmatic activity was the fiery announcement that the world was changing forever. This episode of Earth's history shows that deep Earth forces, massive volcanic eruptions, and the slow drift of continents are all parts of one continuous story. The Proto-Atlantic region was a dramatic, often brutal stage where nature reshaped the planet's surface, gradually carving the map we recognize today. It marked the final chapter of Pangea's existence and the opening act of the Atlantic Ocean, a story still unfolding beneath our feet. Before the mighty supercontinent began its slow, dramatic breakup in the early Triassic, about 250 million years ago, land looked and felt completely different. Imagine a single, enormous slab stretching almost from the North Pole to the South Pole, a gigantic mosaic of crust. No oceans split this land into separate continents as they do now. It was mostly dry, dominated by a harsh continental climate, especially across its boundless interior. The core resembled the desert, with scorching summers giving way to bitter winters, while the peripheral margins were milder and more temperate. Because there were no vast oceans to separate them, animals and plants could spread across huge distances. Early dinosaurs, small, fur-covered creatures related to mammals, roamed freely, and hardy plants could colonize the whole supercontinent. The lack of marine barriers meant life in different parts of Pangea was remarkably similar. Biologically, the world was more tightly knit than today. Beneath the crust, however, powerful forces were already at work. The solid mantle slowly moved under the influence of heat flowing from the core, stretching and cracking the giant landmass. This process unfolded over tens of millions of years. The first signs appeared as massive rifts, cracks far larger than today's East African rift. Within these fractures, magma rose and spilled out as lava, creating extensive fields of dark volcanic rock. These eruptions altered the land and even affected the atmosphere. The early rift valleys were not yet true oceans, but they formed physical barriers. Mountains rose along their edges, and deep depressions hindered animal movement. As the rifts widened and sank below sea level,
Water from the surrounding global ocean, then a single massive sea encircling Pangea, began to pour in.
Shallow seas gradually filled the gaps, carving narrow but significant water corridors across the once continuous land. For terrestrial species, these new waterways acted like vast oceans. Organisms unable to cross them became isolated. Wind-borne seeds struggled to travel, and even birds or insects could be blocked. Thus, the continent was split not only physically, but also biologically. Growing isolation sparked one of evolution's key drivers, divergent development, setting the stage for the diverse life we see today. When a group of animals or plants splits into two parts that can no longer interbreed, each side begins to change on its own. They stop sharing genes, find themselves in different environments, and their structures, behaviors, and traits evolve independently. As the continents drifted apart, some regions moved toward the equator and became hot and rainy, while others drifted toward the poles and grew colder and drier. Every new landmass developed its own climate, vegetation, predators, and challenges. Plants felt the impact especially strongly. The supercontinent supported widespread species adapted to a uniform climate, but the breakup created varied habitats. Some areas received more rain, others turned arid, and many featured different soils. This sparked a wave of new plant forms suited to local conditions. Around this time, flowering and seed-bearing plants began to dominate. Depending on where they lived, they evolved fresh ways to attract pollinators and disperse seeds. Imagine a fern that once covered the whole supercontinent. After a new sea divided its range, the population on one side adapted to dry soils, while the other thrived in a moist tropical forest. After millions of years, they would be distinct species, even though they started out looking alike. Animals underwent equally dramatic changes. Early mammals during the supercontinent era were small, mostly nocturnal, and lived in the shadows of dinosaurs. When the continent split, mammals followed different evolutionary paths. A classic example is the separation of marsupials and placentals. Marsupials, such as kangaroos, give birth to tiny young that finish developing in a pouch and spread across southern lands that later became Australia and South America. Placental mammals, whose young developed longer inside the mother, came to dominate the northern continents of Laurasia, North America, Europe, and Asia. Isolated by growing oceans for tens of millions of years, these groups diversified into the rich variety of modern mammals. Dinosaurs also felt the pull of continental drift. In the Triassic and early Jurassic, they were fairly uniform worldwide, but as rifts widened, different families evolved apart. Giant long-necked sauropods and heavily armored stegosaurs diversified to fit the conditions of their separate continents. In the southern lands, titanosaurian sauropods flourished, taking on many shapes and sizes distinct from their northern relatives. Cut off by vast distances and oceans, each group developed its own survival strategies, shaped by the surrounding plants and predators. The changes reached even the smallest creatures. Rivers that once crossed the supercontinent broke apart, leaving fish populations in isolated water systems that later became new species. Amphibians, dependent on moist habitats, struggled with the arid interior and new oceans blocking their movements, leading to distinct amphibian lineages on each continent. These biological shifts were tightly linked to major global climate changes. As the continents drifted apart, they reshaped ocean currents and wind patterns. The breakup of the great supercontinent created new seas, including the Atlantic and Indian Oceans. This altered the flow of warm and cold waters around the world
and gave rise to fresh climate zones. Some regions became wetter, sprouting tropical forests, while others dried out and turned into deserts. Seasonal swings grew sharper in many places. Plants and animals had to adjust, coping with long droughts, frigid winters, and scorching summers. Rift zone volcanism released greenhouse gases that warmed the planet, but the newly formed oceans later pulled carbon dioxide from the air, helping to cool it again.